what you do is that you get some few aspects of it during the practical section. So practical session, as you are aware, is going to be on 23rd. We are not going to change it. Maybe 23rd, even if two people can find, that's okay. We want to have it done. And we take some few, if we are likely to finish today, or if you don't finish today at all, there will be just the terminologies associated with your reportage, and then how to compare your results with the reference points or the reference. That will be the only thing that we may be left with. And that one, we can tackle it during the practical session. So take note, during a practical session, we may have some little time to deal with all the problems and anything that is left untouched today. Right. So you realize that I'm going to go back to what we started yesterday because I presumed that with the improved neighbor county chamber, almost everybody is conversant with it. But I realized that probably you don't know the basics. And in science, it is usually good to understand things from the basics. Once you understand the basics, you are not likely to forget anything. All right. A lot of things I share with you are just from the fundamentals. Just get your fundamentals right, and anytime it will be easy to remember or to build on. All right. So I'm going to go back and then take you through some of the things that yesterday we hurried through. Because you know that when it comes to the sperm count, it's probably the most important parameter. The doctors, that's what they need. That's what they want. And then even the lab people too, that's all everybody wants. Just what is the sperm count? Forgetting about all the other parameters. So sperm count is very, very important. And we said that we have two major chambers or two major methods. That's the macular county chamber. Unfortunately, many people don't have it. Unfortunately, a lot of people don't have it. All right. So yes, after using the chamber, just wash it. Not in soapy water, just ordinary tap water. Just wash it and it's done. That's one of the simple things about. And with macula, there is no. If you go back to the key points I shared with you, we don't even need anything like accuracy checks. I mean, everything has been standardized. And so just wash it and it's okay. All right. So there's something probably I forgot to tell you, but since someone is asking about the macula, just someone is asking about its availability, just as I said over and over again, suppliers will move or will want to sell items that move. That one, you should understand. No, what they call supplier will bring in item when he thinks that there's no market for it. So as you are going through this program, if a lot of you think that the best way to deal with sperm count is to go the macula way, in fact, that's the standard method. Okay. If 2 or 3 people want it, then you know that you can, if a supplier knows that you can get a market for it, why not? You can get it. But for a supplier to go and bring an item once, even now, as we speak now, if you want the ordinary improved county chamber, you know that it's very difficult to get them. You know why? Because people are not buying the neighbor county chamber because the hematology analyses are now available. Nobody's doing manual, even though yesterday I got the impression that you are doing it. But I'm sure that I can tell you from Konfanache, nobody does manual, WBC count. Nobody does it. The only place they do manual count using the chamber is in microbiology, where you need a neighbor counting chamber to do your cell count. And you can ask yourself, how many CSFs even come in a day or in a week? Okay. And if you go and buy one counting chamber, if you take very good care of it, I'm sure even for 1 year, you don't go and buy another one. So you see that the demand for even the normal county chamber, the neighbor county chambers are going low. And therefore suppliers will also begin to also make sure that, oh, if my last stock runs out, I'm not going to go for another one because the market is no more there. All right. So as for its availability, I'm sure it is dependent on how people request for it. Okay. But if you need it, I'm sure you can get it, even though they may not be readily available on the market. But once you tell a supplier that I need a macula chamber, probably the supplier even haven't seen some before. They can show him a picture. This is called a macula chamber. You can Google and get some information about it. Give it a supply. He buys one or two for you. You begin to use it. And once you begin to use it, students come to your facility and you also take them through these ones. You know that with time, then people catch up with macula. I'm sure yesterday somebody said it's the first time he's hearing about macula. Okay, so it is also true that many people haven't heard about macula, and so you become the advocates. And you know that once you use the macula, it is, I mean, you are not going to do any dilution. You don't need any bicarbonate to go and prepare your diluting fluid. You don't need anything. Okay, right. So I'm sure you are the people to promote the market for it. There's something that I didn't tell you, but I'm sure you may, if I ask you in a question, you should be able to do it, but I don't want to take anybody by surprise. You remember you said that for the macula, you will have the grid or the lines or the squares to be 100. 10 vertical, 10 horizontal. And if you take any 10, a row of 10, any row of 10, okay, when you count the number of cells there, then you add million per minute. And then I said that even sometimes, let me use these are things that makes us waste a lot of time with all this, but I'm sure that it's better for people to understand than to rush through. So you can take one row or one row here, but I told you that you can also go diagonally. I'm sure you remember that one. Good. Whichever way, any row of 10, you can get the result to be whatever value you get, add million per million. Now, if the cells are not too much, please take note. If the cells are not too much, okay, then you see the more the numbers that you count, the more accurate you are with the result. So that you remember that I was telling you, even with the neighbor county chamber, the idea is that the H shape, which gives you a top and a bottom platforms, you are supposed to have used the same sample for both the top and bottom, count each size, and then find the average. It means that the more you do the count and you find the average, the more likely your results are to be reliable. So here too, when the sperms are too scanty, for example, this one, they are not too much. Okay. So if they are not too much, the advice is that you can count the entire, cells within the squares. What will be your results? What will be your results? You can tell me. If you tell me, that it means that you understand the whole thing. I didn't tell you this yesterday, but if you're able to tell me this, then I know that you actually understand what you did yesterday and actually your science is working. I'm saying that if the cells and the sperms are not too much, you don't need to take one row. You can count the entire sperms within the entire 100 rows. And then remember, we said that if you take a row, whatever number you get. If let's say you get 35, it is 35 million per mil. If you had 3, it is 3 million per mil. So if you account the entire region, the entire squares, what will be your results? Somebody to tell me. Then once you're able to tell me, I know that you now understand the principle of the macro and you can apply it anytime, anywhere. If the cells are not too much, you are advised to count everything. In that case, what will be your result? The sperm count, what will it be? Divide total mass by 10. Ooh, that is my guy. Yes, everybody's getting it. O2 and then OT. Yesterday, OT stole the day, and today too is coming out. Fantastic. So that is what it is. So, for example, if I didn't tell you and I asked you this in the examination, then somebody said, "Oh, but you didn't teach us this." But this one is like common sense. Excuse my language. It's a common sense. So if you counted the entire region and you had 100, it means that the 100 should be divided by 10 before you add your million per million. All right, so this means that you now understand the principle of the macro and you are free to go. Very good. Thank you, OT and Co. So we're still going to go through the um, um, neighbor candidate because that is the one everybody knows. And that is the one that, even though it is not the ideal procedure, okay, this is what everybody is using. And therefore, you should understand so well. You should understand it also in a manner that any count at all, whether the sorry, my network wasn't stable. I went off. So back to what I was saying, I'm saying that I want us to take a second look at the Neighbor County Chamber because I overtook things for granted that I know that there are a lot of things that you know about the chamber. But unfortunately, I'm sure you don't have enough information as I wanted you to have. And so you're going to go back. Even if you don't finish, I'm saying that you finish up on the practical session. All right. So with the neighbor, I'm saying that at least, if for anything at all, now everybody understands what is this 0.0025 millimeter square on the chamber. And we realize that it is the area of the smallest square on the chamber, or on the grid. And this 0.0025, which is the smallest square, will be gotten from the central square area. Okay, because it is the central square area where the rulings have made in such a way that the central one areas one millimeter square area has first and foremost been divided into 25. And so it means that each side has been divided by 5. And therefore, once that side has been divided by 5, the size there for each square will be 0.2. Okay, because it's going to be 1 divided by 5. Sorry, 1 divided by 5. And that will give you 0.2. I hope that is correct. Okay. I think I've made more lessons on this. So let me go forward. Then we appreciate it. So here we said that we have 2 types of the chamber. One, the original one, we call the standard type. We also call the inclined, because this one, if you want to charge the chamber, you have to incline, you have to bend your capillary or your pasta pipette in a manner to be able to charge it. This one you don't need. The second one is the V-shaped, the V-load or the V-shaped. Because of the cut out there, you just place the thing there and it goes. So these are the 2 types. So if you get any of them, so don't say that, oh, this one is already cracked. If you don't take care, someone will tell, oh, this one is already cracked. And so I don't like it. But this is the new model which is coming out. And we also knew that the 0.100 millimeter here is also talking about the depth of the chamber, which I'm sure now it is not a problem for anybody. Good. So I've tried to add some few slides. So for example, with the standard type, you see that when you are charging it, you have to incline, you have to bend the, what do you call it? The pipette in a manner to be able to charge it, okay? So this is, sorry. So this is called a standard one or the inclined, okay? Right. Then you come to the V-load. So this is the type, this one, you are just placing your specimen just at this point where you have the V cutout. Okay, so it is, the difference is in the charging mode. Okay, so in this one, when you are charging it, you have to be careful. This one, when you are charging, you can even close your eyes and put this one there and then it goes. So that's the only difference. So the different types gives different charging models. That's all. That's all. Good. Right. Then we're also going to look at, yesterday, I think we looked at this very well. And we knew that once you place the cover slip on it, we also explained that the cover slip, the original cover slip that comes along with the chamber is thicker than the ordinary cover slip you use in our labs. Even though in the absence of the original cover slip, we use the smaller ones, but we must know that the intent is to get a thicker one, which will not compromise its position on the chamber. Once you are using the ordinary cover slip, they are lighter, and if you are, in case you are loading your chamber and you put too much of the specimen here at this place, there's a tendency for the load to lift up the cover slip. Once it tries to lift up the cover slip, what it means is that it is now taking up more fluid than usual. Meanwhile, the fluid that is you are going to charge here is calculated based on the space that's available. All right. Now we said that the rulings, we have 9 millimeter square rulings. And this is what we tried to explain yesterday. So that for the entire platform, we have a 9 square millimeter space. Now, once you have 9 like this, 9 square like this, then you can have a central square. And because you have a central square, the central square will now have corners. So this corner, this corner, this corner. So you have what we call the 4 corner squares. And they are all the large squares. So you can sometimes say the 4 large corner squares. Okay? Because there's different types of squares. Some are large, some are small, some are even smaller. And so this is how the whole thing is like under the microscope. Okay. I think we said that this, where you have your L, is designated to count WBCs. Okay, so sometimes we call it the WBC area. Okay, now we said that the divisions into 16 here is just to allow counting in a more convenient manner, so that if I am, let's say, at this corner, if I'm counting cells in this corner, all right, this large corner, and I can concentrate from one square to the other. Okay, move to the other, move to the then come, so that even if there's any disruption, I know where I am and then come. So the squares are just for convenience sake. Now, over here, remember, please take note. Remember that the original intent of the neighbor chamber was for counting cells, blood cells. You know, when you talk about blood cells, you are having the white cells, you're talking about red cells, we're talking about platelets. Remember, these days you just put your sample into the analyzer and gives you platelet count, WBC count, RBC count. The previously, that was not the case. So you were doing manual RBC count, manual platelet count, and manual, what do you call it? White cell. Manual RBC, manual platelet, and manual listen, and manual white cells. Now, so take note and listen here. We're saying that the divisions here is just to allow for counting. Okay. Now, RBCs, WBCs, and platelets, which is the biggest and which is the smallest? Somebody should tell me. Hematology. RBCs, by way of size, RBC, platelets, and then white cells. Which is the biggest and which is the smallest?
White blood cells are the
Somebody
biggest.
should come up.
White blood cells are the biggest.
RBCs, platelets, and then white cells. Which is biggest and which is, so WBC is what?
The biggest.
If you say WBC is as what? Because I say which is biggest and which is the smallest. So if you say, so, oh, very good. So OT, you are always making me proud. So WBC is higher, bigger than RBCs, and also bigger than platelets. So platelets are smaller. And we are saying that this chamber is being used for counting all the cells, both white cells, red cells, and the platelets. Now we are saying that the division is to allow for convenience sake. So you know that platelets are smaller and also by way of numbers, they are also plenty. Remember that red cells are also at least smaller than white cells, but they're also plenty. So if you want to count them here, for example, RBCs, if you want to count them here, remember that RBCs are counted in something times 10 to the power 12. And then WBCs is counted times 10 to the power 9. Okay, is counted something times 10 to the power 9. RBC is counted something to the power 12. So something to the power 12 means that there are too many. There are, 10 to the power 12. There are many. So if there are many, it means that we're going to have many of them. And look at this space, this square here. You think that if you have many RBCs here, and you are going to count them in this space, do you think it's going to be as easy as you have for white cells? Of course, no. But white cells are bigger, and they are not too many too. And so it means that you can conveniently have them into these spaces and then be counting them. However, if you are going to do the same thing for platelets for RBC, platelets are smaller, and RBCs are also smaller. And so they are going to count themselves here, and at the end of the day, you can't count them. So what it means is that you need another area where the squares are smaller. So that once the squares are smaller, it means that they can you can concentrate on it and be able to count the number of cells there. So you realize that the divisions here are different from the divisions at the center here. Remember, you said that the divisions here is divided into 16. Here, first and foremost, divided into what? first and foremost divided into 25. So once they have been divided into 25, what it means that the squares here are smaller. And once they are smaller, it means that the smaller cells can be accommodated there. So in effect, the central area here, it was designed to count red cells and platelets. I don't know whether you are understanding me. The divisions here are much smaller because you are going to count cells which are smaller. And once they are smaller, the number of squares should be smaller so that you can conveniently count them. So this larger area is designed for WBCs, and this central area is designed for RBCs and platelets because their numbers, their sizes are smaller. And therefore, if you want to put them in this bigger area, you counting, you still be confused because because they are smaller. You are going to count themselves here, and then counting becomes difficult. So the essence of the central area was designed for RBCs and platelet count. All right. Now, we've also said that because this place is divided into 25, it means that each size here we can calculate. And that is what we did. Let's go to the next slide. That's what we did. So the same thing here. So this size, remember I've changed this picture here because yesterday I realized that even from the picture I took from the internet was wrong. Remember, we said that this place should be divided into 25 here. So this is 1, 2, 3, 4, 5. But the picture I showed yesterday here was 4 here and it was also 4 here. So it means that that picture is also wrong. But unfortunately, it's been posted on the it's available on the internet. All right. So this place is divided into 25, and therefore each size has been divided by 5. If we divided by 5, it's the same 1 millimeter because we said that this are squares. So if they are squares, it is this size is 1 millimeter. It means that this side is also 1 millimeter. And therefore, for each of these small sizes, it is going to be the 1 divided by 5 and not 4, because we're saying that this side has been divided into 25 squares. Therefore, each side has been divided into 5. And therefore, to be 1 divided by 5, and that will give you this 0.2. Okay, this 0.2. Now, somebody asks, what is this 0.005 here? Now, remember, we have neighbor county chamber and improved neighbor county chamber. All right. So the original neighbor county chamber had the lines 1 row like this. Okay. The improved neighbor county chamber tries to make sure that for each boundary, the one line is made 3 lines, so that you know that once, because if you are counting, and if you are not experienced, and you know that you are counting 4 here and then 4 down, once you are counting along, if you don't take care, you count 1, 2, you may not count the 1, 2, 3, 4, but once you are counting the cells, you are likely to go and then also count the cells here, because there's a picture. But under the what do you call it? Under the microscope and with the actual chamber, this one doesn't end abruptly, so that you have some squares also here. But it is up to you to know that you are dealing with 16 squares, so you don't have to go beyond 4. So the improved county chamber brings about this concept of giving you impression that, Master, you have ended, so that once you are counting 4 cells, 1, 2, 3, 4, and let's say even you forget, as soon as you reach here, you know that here the lines are duplicated. So once the lines are duplicated, it tells you that you have gotten to the end, and therefore you don't have to go beyond. So for example, this is a single line, this is a single line. But if you get here, you are getting 3 lines. And those 3 lines is just telling you that, Master, you can't go beyond this one when you are counting. So that is the difference between the neighbor county chamber and the improved neighbor county chamber. The improved neighbor county chamber has triple lines to demarcate each end of the rulings. I hope my point is clear. And that this the 0.005, they think that it's insignificant. So if you are cutting lines, that will just be 0.0005. It is insignificant, and therefore it gives you the same one line which has been in triplicate, but still within a boundary of 0.005, which is insignificant. And so I'm hoping that somebody is understanding me, that this is the difference between neighbor county chamber and improved neighbor county chamber. With improved neighbor county chamber, the lines have improved so that you don't count beyond a certain, only to count. Hey, sorry, I shouldn't have counted the cells in this square. I've counted over and above the 16. So this is to help you to know your limit. I hope that point is very clear. Right. So over here, you get your 0.2. And this within the 0.2 has also been divided into 16. And so once it has been divided into 16, it means that 0.2 has been divided into 4. So it is 0.2 divided by 4. And that will give you 0.05. Is that correct? 0.2 divided by 4. What will you get? You get 0.05. Is that right? Good.
That's right.
So it means that this small square here is 0.05 multiplied by another 0.05, and that is going to give you the 0.00025 millimeter square, which you find on the on the chamber, to tell you that this is the smallest square you can ever have on the chamber. And these are some interpretations to it. So we have the central large square is divided first and foremost into 25 small squares, which gives you a size of 0.2. And therefore, it will give you an area. This area will give you an area of what? 0.04, because this is 0.2, this is also 0.2. So this here is going to give you 0.04 millimeter square. I hope that point is clear. Right. I think yesterday I have to add all these things to make sure that you are getting these things more clearly. Right. So you have the central area here, which we are now going to concentrate, because all this while, all we know is that the sperms can be counted in the area where you used to count the white cells. Here, 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 and here. But I'm going to show you that sperms can also be counted in a central area in a very unique way. And so you have to know the calculations that goes on within the central area here. All right. And once you understand the calculations that go on the central area, next time you will not even count the square, you will not even count sperms here. You will not never count the sperms in the corner squares, because they look very, very, you have to, there's a lot of calculations here. When we have taken you through the calculations in the central area here, you prefer to use the central area more than the corner squares. So let us understand it once and for all. So it is all the tokens that are made. This is what it is. So we have, in effect, the central area has 400 smaller squares, because the first one is 25, and each of the 25 has been subdivided into 16. So you multiply 16 by the 25, and you're going to get 400. And it is this 400 which you know that each size of the 400 is 0.05 millimeters. And therefore, the area there becomes 0.05 multiplied by another 0.05 to give you this 0.0025 millimeter square, which I've said over and over again that it is written boldly on each chamber. All right. So the neighbor county chamber designated areas for counter sperms. So all we know is that where you have the WBC, WWW, these are the areas that we know can be used for counting sperms. Remember, I've told you that originally the central region, not central region as in Cape Coast, the central region of the chamber was actually designed to take care of platelets and RBCs. Okay, so where you have the P is designated for, in some books you get RRR. So the R is standing for RBCs. And then the P is also stand for platelet. So the W is standing for WBC. So it means that for the normal neighbor county chamber, you have these corners as your WBC area, and you have these regions, and you want five of the smaller regions within the central region. And so to make it more representative, you will have it 4 at the corners and 1 from the center. Okay, to give you 4 representatives, 5 representatives. So the same thing is happening here. So this SSS is supposed also to be used for sperm count. And you remember that the SSS was actually for platelet. And so you have to be able to know the calculations that go on there, because when you're using it for platelets, you necessarily have to do a calculation to be able to get your platelet count. And so what must be the calculations that you must know to be able to do your sperm count? So once you want to get these things, I'm sure when you get there, you appreciate it better. The same thing is happening here. So for the normal county chamber, the designated areas for counting is either the WBC area, which is either 1, 2, 3, 4 corner squares, or the area originally designated for platelets or RBCs. Okay. Right. Yesterday we talked about the tally counter, and then we also talked about the dilating fluid. We said that you need 5% sodium bicarbonate in a formalin reagent. And we said that it is 5%. So 5% means 5 grams of the sodium bicarbonate in 100 ml of water. Now, once you have finished that, you are going to add 1 ml of formalin. The 1 ml of formalin is just serving as a preservative. All right. And the formalin is the 40% formaldehyde. That is normally when you are using formalin in our labs, it is 10% formalin. But it's supplied is 40% formaldehyde in a solution. That 40% is regarded as 100%. I'm sure this one you know already. And so if you are preparing 10%, you take that 40% formaldehyde or formalin as though it is 100%, and then prepare your 10% up from it for your histopathology 10% formalin that you know. Okay, so that is that. Now it is not the 10%, it's rather 1 ml of the original formalin. Okay, this is 1 ml of the original formalin. All right, so that's what you're going to do. So 5% means 5 grams in 100, and I've said that that's the fundamental. 5% means 5 grams in 100 ml. So it depends on how much you want to prepare. So for example, if you want to prepare even 50 ml of your sodium bicarbonate solution, then it means that you divide the 100 by 2. You are going to get 50. And what must you do? You must also divide your 5 by 2. You are going to get 2.5. And you must also divide your 1 by 2. You are going to get 0.5. So you are going to have 2.5 grams of the sodium bicarbonate dissolved in 50 ml, and then add 0.5 ml of the formalin. And that is also good for you. If, let's say, you want to prepare even 1 liter and then be probably distributing or selling to people, then the 1 liter will mean that this 100 must multiply by 10. If you multiply the 100 by 10, you are going to get 1,000 ml, which is your 1 liter. And then you must also multiply your 5 grams by 10. You are going to get 50 grams. And you also multiply your 1 ml by 10, you are going to get 10 ml. So in effect, you are going to get 50 grams sodium bicarbonate, 1 liter of your distilled water, and 10 ml of formalin, and that is it. So you get 1 liter, and then either you want to distribute to people or you want to also be selling or keep it as a stock for your lab. That is it. So this one, please don't go and buy. If you get the sodium bicarbonate, you can use it for the next 5 years. And then you can be preparing, and then if you want to be selling to people who don't know, you only label as uh, um, semen directing fluid. So you so that nobody will know what the composition is. And probably sometimes that's what people do. Then they write uh, seminal fluid, directing fluid, or semen directing fluid. That's all. You can make some designs on it and make it nice, and then be selling to people who even want to buy saline. Want to they can't prepare saline in their labs. They want to buy saline. So those people, I'm sure, if you are preparing your directing fluid for semen, and they will buy like hell. All right, so that is that. I'm sure now it has become more explanatory than what we did yesterday. Or just a build up on that. Remember yesterday we said that in the absence of your directing fluid, you can use clean water, tap water. And we said that in that case, if you want, the water will take a long time for it to kill the organisms, the sperms. So what you do is that you apply the principle that was used for the macula, where the sperms is exposed to 50 to 60 degrees water bath, and that will kill. So once you kill it, when you add the water is just going to be like a diluent. That will, but it's not as proper as the bicarbonate, but the bicarbonate will break up all the mucus, everything to make it more uniformly homogeneous. But the water sometimes it makes it still a little bit clumpy. But that is when probably you really got to know that you've run out of your directing fluid and there's sample to work with. So that is where but don't make it like you're routinely using tap water as your directing fluid for your saline. Sorry, for your semen. Remember, we also said that after preparing your reagent, you can add a little bit of either crystal violet or Gentian violet, as you did for your text fluid. Remember, we said text fluid is the WBC directing fluid. And unfortunately, as of yesterday, I'm sure a lot of people didn't know that the WBC directing fluid is called text fluid. So you prepare your 2% or 3% acetic acid. And you see, sometimes people we ask somebody, so um what is the reagent used for WBC counting? They will tell you 2% glacial acetic acid. That is wrong. Okay, for example, if you prepare 70% alcohol, can we say 70% absolute alcohol? You can say that. You use the absolute alcohol to prepare your 70%. Once you have used the absolute alcohol to prepare 70%, your 70% is 70%. You can't say 70% absolute alcohol. So glacial acetic acid is the concentrated acetic acid. Once you have used it to prepare your 2%, you can't call it 2% glacial acetic acid. Okay, so there are small things that we say technically that is incorrect. So we need to take note of some of those things. So you prepare 2% acetic acid and then change it with either crystal violet or ginseng. And I'm saying that changing is just to give us a small coloration, and that color is supposed to be able to try to stain the nucleus. So, all right, not staining it in the proper sense of the word, but gives a little color so that they stand out. So the same thing with the semen. Once you finish preparing your bicarbonate formalin reagent, you can change it with crystal violet a little bit. Okay, also to give some kind of a shine to the sperm so that when you're looking for them, they look nice to you. All right. Right. So this is where we ended yesterday. So we're going on why semen samples should be diluted for counting. Why should it be diluted? Remember that we said over the macula, there's no dilution. You don't dilute you don't, yes, there's no dilution, there is no reagent to add, nothing. But with the neighbor county chamber, you have to dilute. Why must you dilute? Let's look at the reasons why dilutions are important too. So there is usually large numbers of sperm in the semen sample. It is necessary to dilute the specimen to obtain manageable numbers for the sperm counting process. Okay, right. The numbers are usually many. I mean, remember some semen can contain as much as even 200 million per male. Okay, now so the numbers are too much. If they are too much, they can overwhelm the entire chamber, so that you can't even count. But as you dilute, I'm sure the other day we talked about proton effect. Do you remember? When it's a proton effect, when there are too much antibodies in the system, they tend to give you, when you are doing antigen antibody reaction, they tend to give you a negative result. Okay. Now, so if that is the situation, the antibodies are there, yet the result is negative. If you are suspecting that there is a proton effect, what you do is to dilute. Once you dilute, you are reducing the numbers of the antibodies, so that now they can proportionately react with the antigens and give you a good result. Okay. Now, remember, we also said that sometimes not just only the numbers of the antibodies. You can tell me what else could cause proton effect, even though, but we are still learning. So let us go back. So sometimes it's not just the antibodies. If the antibodies are too much, that overwhelms the antigens reaction, they give you a proton effect. What else can give you a proton effect? Yes, you can tell me. Yes, please don't disappoint me. I'm sure we did this one when we were doing the syphilis serology. Please don't disappoint me. Somebody should come. When you have too much antibodies overwhelming the antigens, the reaction will be negative. And that's what we call proton effect. In that case, you dilute. Once you dilute, you are reducing the numbers of the antibodies. I'm saying, what else, apart from the antibodies, can also give you a proton effect? Oh, forgot the name. Remember, we talked about interference substances. Sometimes the antibodies are there, but there are also interference of sometimes that look like like the less antibody, but they are not the true antibody. They block the antigen antibody reaction. So if there are interference substances and you also dilute, as you dilute, you're also diluting out the interference substances to give way for the rare antibodies to also react. Okay. So what I'm saying is that once you do a dilution, the antibodies or the substances of interest the numbers will reduce. So we're saying that why do you have to dilute? So we are diluting because sperm numbers are usually huge. And once they are so much, if you do, if you dilute, okay, if you dilute, the numbers will come down and then you are going to get a manageable number to count. Somebody, don't ask me what about the macula. If you talk about the macula, you see, I want somebody to go and read on this one and then come in. Okay, unfortunately, we are not going to come back. If you saw the picture of uh, the what do you call it? Of the macula. Do you see the depth of the macula? Do you remember? Or you didn't see? You can tell me the depth of the macula. the depth of the macula. You didn't take notes, and it's likely I can ask you in your exams. The depth of the macula is 10 microns. You didn't look at it. Look here. I hope somebody's responding. Very good, Andy. That's excellent of you. So the depth of the, let me take my, today we may not finish, but don't worry. It is better to understand everything rather than rush in there. If you don't finish, I'm saying during the podcast session, I'll make up. You see, this 10 micrometer deep. Okay, 10 micrometer deep. What is the what do you call it? The depth in a country chamber. The depth in a country chamber is 0.1. What is 0.1 in terms of microns? Yes, 0.1 in terms of microns. I want you to be very, very scientific so that you understand things in a manner that you say, now I understand. Because once we say that, oh, this one, you are not going to, you don't have to dilute. I'm sure somebody was going to ask, so then why is it by the country chamber, for the macro country chamber too, we didn't dilute yet to be able to count. So this is 10 micrometer deep. Remember the county chamber for the neighbor county chamber has a depth of what? 0.1 millimeters. 0.1 millimeters is how much? In micrometers. Yes. Somebody should come. This one there. Don't Andy. Don't disappoint me. So what will be the depth in terms of micrometers for the neighbor county chamber? The depth of the neighbor county chamber is 0.1 millimeters. This one is not giving you millimeters, it's giving you in micrometers, 10 micrometers. So you must, to be able to compare, you must also convert the depth of the, what do you call it? The neighbor county chamber also in micrometers before you can compare. You can't compare apples and oranges just like that. This one is in micrometers. The other one is millimeters. So you must either convert this one to millimeters or convert the millimeters also to microns so that you can do your comparison. And I'm saying that what is the value in micrometers as far as the neighbor county chamber the depth is concerned? This one too, that should be a problem. Yes, who is coming? The depth of the neighbor county chamber in micrometers. Hello? Oh, okay. Convert 0.1 millimeters. Convert 0.1 millimeters. Okay, so Andy, you are correct. Well, where were you? Where were you? So please, ladies and gentlemen, don't leave this one. These are basics. So they are basics which students come to your facilities. These are things that you should tell them or teach them. Okay. So if this one has a depth of 10 micrometers and that one has a depth of 100 micrometers, what does it mean? It means that this one will accommodate more layers of space for the sperm to for more sample, or for that matter for more of the sperm. That's what it is. So you must be scientific. So this one having, when you put the sample there, the macula will make sure that it slash off all the unwanted specimen and leave it just 10 micrometer deep, so that it is able to reduce as much as possible the sperm that must be there. This one has a depth of 100 micrometers. So it means that you can, that's why when you are doing a count, please take note of some of these things. That's why when you are doing a sperm count or a count, you keep on changing your fine adjustment. You don't know why, because the 100 micrometers or the 0.1 is a lot of space. And so the sperms may be lying at different phases. And so as you keep on fine-tuning, even as you count, you keep on fine-tuning, then you'll be seeing some cell will be lying up, some will be lying low, some will be lying medium, that kind, so that you can have the benefit of counting them. So if you are a scientist and you are doing a sperm count or any count like this, and then you focus the thing and then just on one plane, master, you are joking. You are joking. Because that depth is a lot of space for some cells to be lying at different planes. So that's why you have to keep on adjusting the distance. So even as you are counting, you are still manipulating your what do you call it? Your fine adjustment, so that you can be looking at the specimen from different planes. All right, that's what it is. So with the macula, it has a depth of 10 micrometers, and that is significantly going to reduce the volume of sample, and for that matter, the number of sperms, to a manageable, what do you call it, to a manageable count. I hope that point has been cleared. All right, so let's go back to where you are coming from. Okay, so we make the dilutions to be able to make the numbers manageable to count. All right, so we also make the sample less viscous to allow the suspension enter the chamber smoothly by capillary action. I'm sure all of us know about capillary action. Remember that with the macula, you deliver the sample into the center area like I told you, and then before you apply the cover slip. If it's a cover slip anyway, before you apply the cover. Okay. In the case of the neighbor chamber, you apply your cover slip first. Okay. And then you are going to apply the specimen through the edge, the small space there, the 0.1 millimeter space there. That is going to serve as a capillary action. You know, a capillary action is the capacity of a fluid to move through a small space. Okay. And then on its own. So it's like when we have a capillary tube, we put it in the water. We don't need to suck. Instead, the water itself will put itself into the capillary tube. The same way, if you put the same capillary tube into blood, say blood will move into it. But the two of them, which one will move? I mean, the fluid will move quicker. If you put capillary tube in water, and the same capillary tube is put into blood, which of them will move faster? Yes. Yes, I need your answers. You put capillary tube in blood sample, you put capillary tube in water sample. Which one of them will move up higher or faster? Water. Why? Because water is less viscous. So what it means is that the movement, the capillary action, is influenced by viscosity. Okay, so the less viscous the sample, the much easier will it move through capillary. And so we are saying that you have already applied the cover slip and you are letting the sample flow by capillary action. So it means that viscosity is going to play a role. Now, all of us know that semen is viscous, even when it has liquefied. That's why after liquefaction, we do the viscosity test. So every viscosity is about thickness or how sticky something is. We've done this already. So if you know that semen is viscous, and you want it to flow through a chamber by capillary action, And you think that if you don't do anything about it, it will move. It will move because it is viscous, and the capillarity action is influenced by viscosity. And over here, you see, even if you take the normal capillary tube, it may have a ball size of about 1 millimeter or something 1.5 millimeters. Okay, this one has the space under the chamber is 0.1. 0.1 is 1/10 of the smallest capillary tube you can have. The smallest capillary tube will have a ball of, let's say, 1 millimeter. And so you are going to have, so it means that the ball, the space available for the thing to move is so small that if it is not made less viscous, it will just not move. These are the science, these are the principles. So apart from if somebody says, oh, if the sperms, okay, what if the sperms are not too much? You're already, even if the person is very acute oligospermia, we say that you want to dilute so that the sperms become manageable. What if the patient is even azoospermic or very low count? Do you still have to? What do you call it? Do you still have to dilute? Yes, you have to dilute because for as long as you want to charge the chamber, the space available for the chamber to allow fluid to move is too small. Said that viscosity plays a huge role. That's why I'm saying that if you put a capillary tube in water and a capillary tube in blood, which one of them, and all of you agree that the water will move faster because of viscosity. The blood is more viscous than the water. Okay, so you need to bring the viscosity of the specimen close to water, if not equal to water, close to water. And that can only be done by dilution. So that's also one of the reasons that you have to dilute. All right. And then prevent overlapping of sperm cells in the chamber to facilitate. So when the sperms are, once you dilute, the sperms become a little bit more scanty, and therefore they can be lying on their different positions for you to be able to count. Okay. And then here we dilute to immobilize the sperm to allow for their counting. So remember we said that the bicarbonate will do two things. One, to kill the organisms or the spermatozoa, and also to make the specimen itself, the seminal plasma, also less viscous. Okay, so the dilution is also to do the immobilize, to make the sperms stable for you to be able to count them. So these are the reasons why you have to do the dilution in respect of the neighbor counting chamber. Sorry, in respect of counting sperms using the neighbor chamber. So if you are diluting, then what is it? What must we know? We must know what we call dilution factors. Dilutions and dilution factors. So in effect, dilution factors is how much of a sample is in a suspension. Okay, how much of a sample? For example, if I take, this one is not on the slide, but listen to me and answer me. If I take 9 mL of, let's say, saline, and I add 1 ml of blood to the saline, what volume do I have? I've taken 9 mL of saline, and let me say, instead of blood, let me say serum. And I adding 1 ml of serum to the 9 mL of saline. What volume do I have? This one is like class one. This
10.
10 mL. The question is, out of the 10 mL, how much of the sample is in the 10? Out of the 10, how much of the sample is in the 10? It's 1, very good, Ramsey. So here we say that it is 1 in the 10. 1 in the 10. So 1 in 10 becomes your dilution. Okay. Now, Elvis, are you the one who told me that yesterday that you were doing the manual WBC count? I'm sure you were the one. Yes. Okay. So in manual WBC count, hey, who is asking this question? Albert, I want somebody to answer Albert for me. It means that yesterday you were not in class. Definitely you were not in class. I won't answer this one. Either somebody answers him for you, for him, or I leave it. I'm not going to answer this one, please. Really, you have exposed yourself that you were not in class yesterday, Albert. Good. So somebody can answer him, but I'm not going to answer this one. Right. So in the manual WBC count, you take 20 microliters of blood sample. Listen to this, everybody is also a work for everybody. You take 20 microliters and write this one. That's for the manual WBC count. You take 20 microliters of blood sample and you take 0.38 mils of the text fluid. All right. You take, everybody write it somewhere and work it out for me. I need an answer. For the manual WBC count, you require 20 microliters of blood, whole blood. And you also require 0.38 mils of the text fluid, or what you people call the WBC dilating fluid. When you do that, what is your dilution? What dilution have you made?
One in 20.
Hey. Right, you have given a wrong answer. Add 1 part of water to 2 parts of semen, put it in water bath, please. So I didn't say that for the macula. The person is asking a question about how do you immobilize this thing for the macula. Albert question, please, how do you immobilize the sperm if you are using the macula? Right, your answer is wrong. Oh. Good. OT is actually making things easier for me. But of course, if it's one person who is doing this one, it becomes problematic. Because how do I know that everybody is? How do I know that everybody is also in tune with it? So unfortunately, okay. So OT, you are very, very correct. That's very correct. I wish that everybody understands it. So 20 microliters of the blood sample, when you add it to 0.38 mils of the WBC diluting fluid, if you want to work out the dilution, what you do is that one is in microliters. You know, the blood is 20 microliters. And the diluting fluid is in mils. So first you have to convert the mils also to microliters. Okay. The mils is 0.38 mils. When you convert to microliters, what will it be? Yes, somebody should put it up. Not OT. OT, you have done so well. So the 0.38 mils of the diluting fluid. No, 38 is wrong.
You get 380.
0.38 mils of the diluting fluid. Yes, 380. So 380 microliters. So if you have 380 microliters, then that's with the diluting fluid. So you add the 20 microliters of the sample of the blood. So you are going to get 400 microliters of the suspension, because you have 20 microliters of the blood and you have 380 microliters of the diluting fluid. So if you put the two together, you have a total volume of 400 microliters. The question is, how much of the sample is in the 400? This is 20 in the 400. 20 in 400. And you know, mathematically, in is a ratio. So if you say 20 in 400, 20 over 400. So if you have 20 over 400, if you work it out, you are going to get 1 over 20. Now 1 over 20 becomes your dilution, which is 120. These are the fundamentals, ladies and gentlemen. These are the things when students come to your facility, these are the things you have to let them know. Okay, so whenever you are making dilution, the question is, what portion of the sample is in your total suspension? That's all. That's the question to ask. So you are taking a certain amount of the sample, you're taking a certain amount of the diluent, you have put them together to get a certain suspension. Then you ask yourself, how much of the sample is in this suspension? That's all. Then you work out the dilution, and you know dilution is always 1 in something. So you have to work it out to get you a value of 1 over something or 1 in something. I'm hoping and believing that somebody is listening. Good. So the best way is that if you're doing any dilutions, you determine what dilution you want to do. If let's say it's 1 in 4, if it's 1 in 4, then you know that in mathematics we have what called distributive properties. Do you remember associative properties, distributive properties? So if you want to do 1 in 4, it means that you are going to get 1 part of this and 3 parts of the other to give you the 4. So 1 in 4 means, I'm going to make 1 in 4. It means that my total volume should be 4. And the addends, the things that I'm going to add should give me my total. So, and the things that I'm going to add to the 1 is constant because it's always 1 in something. So if I'm going to do 1 in 4, I want a total of 4. And my 1 is constant. So what is going to be the middle one? The middle one is going to be 3. So it means that it is 1 part of the sample and 3 parts of the diluent. Okay, 1 part of the sample and 3 parts of the diluent to give me my 4. So if I have 1 and I say even the 1 is 1 ml and my 3 parts is 3 ml, then I'm going to get 4 ml. After the 4 ml, how much of the sample is in the 4 ml? Is the 1. So it gives me a 1 in 4. Now, so once you have this understanding, you can always manipulate it anyhow. So if I want to do 1 in 4, I can decide, okay, I know that 1 part of the sample and 3 parts of the diluent. So that's the fundamental 1 part and 3 parts. I can decide to make my 1 part, let's say 2 drops. If I make my 1 part 2 drops, then my 3 parts will be how many drops? Yes. I want to make 1 in 4 dilution. It means 1 part of the sample and 3 parts of the diluent. I say my 1 part is 2 drops. What is going to be my? Yes, it's going to be 6. So if you have 6 drops, and then you have 2 drops from the from your sample, in total, I'm going to get 8 drops. The question is, how much of the sample is in the 8 drops? It's the 2 drops, so it is 2 in the 8. 2 in the 8 means 2 over 8. If you work it out, you're going to get 1 in 4. Simple. If I decide to say that, okay, my 1 part, I want to do 1 in 4. I say that my 1 part is 0.5 mils. Okay, my 1 part is going to be 0.5 mils. What is going to be my diluent? I want to do 1 in 4 dilution. 1 in 4 dilution means 1 part to 3 parts of the diluent. 1 part of the sample, 3 parts of the diluent. If I decide to make my 1 part 0.5 mils, what is going to be my diluent?
1.5.
1.5. Fantastic. So once we know these things, it makes it easy. Dilution factors are usually very easy, and it's not like constant, always do it this way and do it that way. It depends on how you want to do it. And how you want to do it depends on your understanding of the whole principle. Okay, so with this one, 0.5 plus the 1.5 will give me 2 mils. Okay, after the 2 mils, how much of the sample is in the 2 mils? It is 0.5, so it becomes 0.5 over 2. If you work it out, 0.5, because it's also a fraction, a decimal, you have to make it the whole number. So you multiply the top by 10, you are going to get 5. And you multiply the down by how much? Also by 10, and you are going to get 20. So you're going to get 5 over 20. If you work it out, you're going to get the 1 in 4. So just understand it from the basics, and you will always be able to get it the way you want it. The way you want it. So, for example, you want to make 1 in 20 dilution. Here it is 1 part of the sample to 19 parts of the diluting fluid. So you can decide. Normally with semen, we are comfortable using drops. Okay, we are comfortable using drops. So it means that I'll take 19 drops of my diluting fluid, and I'll take 1 drop of the semen, and I'm going to get 20 drops. Out of the 20 drops, I have 1 of the sample in the 20. That gives me 1 in 20. If somebody decides to make it make the the 1 part, make it 10 microliters, for example. If you want to make it 10 microliters, then the 19 parts will be what? 19 10 microliters, there's going to be 190 microliters. 190 microliters is going to be 0.19. Sorry, it's going to be 0.19 mils, something like that. Okay, so any way you want to do it, please, it is in your court. Dilutions are always in your court, the way you want to. When you say 1 in 20, means 1 part to 19 parts. If you want to say 1 in 100, it means that 1 part to 99 parts. And then the 1 in 100, 1 part, that doesn't mean that it is 1 mil plus 99 mils. You are going to get 100 mils. And out of the 100 mils, you get 1 mil in the 100. Fine. But that 100 mils that you have prepared, what are you going to use it for? If at the end of the day you are only going to use some 1 drop to do your suspension, why have you prepared 100 drops? So you have to make a determination that I need 100. But what should be the best way? Okay, you can decide that, okay, if it's 100, I want 100. I can decide, like I made the first example, my if it is 0.1 mils, 0.1 mils, then my 99 part will be what? Be 9.9 mils. Okay, the 99 parts will be 9.9 mils. So in all, I'm going to get 10 mils. 10 mils. Out of the 10 mils, I have the 0.1 in the 10 mils, and that is equal to 1 over 100. The question to is that do I see even the need 10 mils? If the 10 mils, so you can still work it out to get appropriate volume, which still has the same effect as the dilution factor that you want, if you understand it. Okay. Thank you. I think we've talked a lot, and I'm sure that you understand it. So in effect, dilution factor is the sample over the total. The total, where the total is the sample, the sum of the sample plus the diluent. Okay, and I think we have done a lot of examples. So this one, a sample of 0.05 or 50 microliters. If you add it to a diluent of 0.95 mils, what are you going to get? If you work this out, you are going to get 1 over 20, which is your dilution. Okay, right. So you should be able to work a lot of examples on dilution factors. Okay, let's move. And there's like a table to help you. When it comes to semen, okay, remember we said that we always would do an initial microscopy, where after the liquefaction. Remember, we said that when sample comes, the first thing is the volume. Why the volume? Because the volume, you don't need to wait for it to liquefy. And the volume, we recommend the weighing method. The weighing method or the weight method based on density will require that you pre-weigh your container, and then you also weigh the post-coital container. And then the difference becomes your weight of the semen. And the weight of the semen is equivalent to the mils of the semen based on the 1 gram per mil density of the semen. This is, you have gone beyond this. Immediately after that, you do your pH, because we don't want the sample to lose a lot of carbon dioxide, which will at the end of the day give us higher pH we have talked about. So you do your pH. The next thing is to do your microscopy. The microscopy will give you a good idea about the movement, and then together with what dilution to make. Remember, we mentioned that the microscopy, the initial microscopy you do is also going to give you an idea about what dilution factor you need to work with. And this is supposed to guide you. If you have less than 10 sperms per high power field, just 1:2 dilution will do. 1:2 dilution means 1 part of the sample and 1 part of the diluent. 1 part doesn't mean 1 drop and 1 drop. We are talking about 1 part. So you can give the 1 part, let's say 50 microliters or even 0.5 mils. If you do 0.5 mils of the semen sample and you do 0.5 mils of the diluting fluid, that will give you 1 mil. Out of the 1 mil, how much of the sample is in the 1 mil? It's 0.5. 0.5 over the 1. If you work it out, you are going to get 1/2, which is 1:2. If the sperm is between 10 to 15, you are advised to do, let's say, 1:4 dilution. And as I've said over and over again, as 1:4 dilution, how do you want to make it? You can make it 1 drop and then 3 drops, or 2 drops and then 6 drops, whichever way you want it. All right. If the sample sperms are between 15 to 40 mils, you recommend that you do 1:10 dilution. If it's more than 40 per this, you recommend that you do 1:20 dilution. If the sperms are more than 200 per field, you recommend that you do 1:40. So with this guide, you can always do a dilution that will fit for purpose. All right. Procedure for sperm counting. Assembling the counting chamber. This one you can just read before you use the hemocytometer. I'm sure you know the hemocytometer. That's the neighbor counting chamber. Hemocytometer, hem means blood, cyto means cells, blood cells, meter means measurement. So that's hemocytometer was not just for WBCs. It was meant for counting cells in the blood. Hemocyto, in blood, cyto means cells. So the blood cells measurement, meter means measurement. So that's why I'm saying that the clinical counting chamber was not just for counting by cell, counting for cells in the blood. It included platelets, included white cells, included the red cells. And then you just a few minutes ago, we talked about where even to do the platelet count and where to do the RBC count and why. Because they are smaller and therefore you needed smaller squares to be able to make the counting more manageable. Okay, right. So that's for the hemocytometer. So rinse them in water to remove any dust particles. Do not use soap. Gently wipe the chamber and cover glass with soft cotton. Do not use paper towels or cotton wool. Place the cover slip in position. Moisten each side of the grade areas and affix the cover slip. Remember that we said that as compared to the macula, the macula you charge the chamber, you put in the specimen before you apply the top, the cover. Here with the neighbor chamber, you apply your cover glass first. The cover glass must be made in such a way that it actually affixed onto the chamber, so that because you must fix it, normally you use just some small, you moisten your hand, and then the grade, what do you call it, the pillars on each side, you just apply some, not too much water, just moisten the area, and then you try to push the cover slip over it. This is something probably in practicals we can demonstrate for you. You push over it. Once you do that, it gets the cover slip affixed onto it. You don't want a situation where you just put the cover slip on it. If you put the cover slip on it and you lift the chamber, you see that it will just flip off. It might be affixed because we said that we want a depth of 0.1. If it is not affixed on it, it means that that depth cannot be, how do you call it? Cannot be guaranteed. It's just covering. It's just covering. If it's just covering it, it means that that 0.1 depth can be compromised. But if you are fixed on it properly, it means that that 0.1 depth is also can be guaranteed. All right. So then, when you have done that, you are going to now introduce the sample into the chamber. Introducing sample into the chamber is described as filling the chamber or loading the chamber or charging the chamber. So you can, so I say charge the chamber or load the chamber or fill the chamber. Any of them can be used interchangeably. Right. So a transfer pipette or micro pipette or dropper may be used for this process. Okay. Now mix the suspension well. That is, once you have already, based on your initial microscopy, you have determined what dilution to make, and now you have made your dilution. If you decide to make 1 in 10 dilution, and if you want to use drops, then it is 9 drops of the diluting fluid plus 1 drop of a well mixed semen sample. 1 drop, you add it, so you get 10 drops. After 10 drops, it is 1 in the 10. That's 1 in 10 dilution. So that is your suspension. This is what we are going to now transfer onto the chamber. So mix the suspension well, transfer 1 drop of the cell suspension from the pipette. You are using a pipette, or if you have a macro pipette, then that one will take exactly 10 microliters. Okay. And then try to, as depending on whether you have a V shape or the standard chamber, you try to push it at the edge, and then it will just move on its own by capillarity. Good. So as we have it here. So this one is the V-shaped chamber. So once the V-shaped chamber, I mean, just put a sample here to move by itself. If it is not V-shaped and it's the standard one, then you must take care. You are delivering a sample at the edge here and to move on its own through capillarity, and then to go. So once that has been done, you allow the chamber to lay on the bench for about 3 to 5 minutes. This is just to allow the cells to settle, because remember we said that in here the cells we're talking about the sperm cells. Remember we said that the depth is 0.1. Okay, and then it has a large area. Okay, and the suspension, the cell suspension is going to fill it. So the cells are all, for them, my sperms are all suspended. So they will have to take time for it to settle. If they don't settle, and you begin to count, you see that by the time you finish counting, some sperm, which is probably in a certain square up here, may have also drifted to the second square area, and you are going to count it again to make it 2. All right. So you allow it to settle so that, I mean, movement of sperms, and even if it was very busy, the movement of cells will have ceased, so that once a cell is counted, it is unlikely that it is going to move to another portion for it to be either lost or recounted. Okay. So place the hemocytometer onto the microscope stage. Count sperms in the 4 corner squares of the chamber in the area designated for Dory visits. I'm sure this one we now know very, very well. Do not allow the sample to settle too long in the chamber, as doing so will cause the preparation to dry out, concentrating the cells over the grain. What it means is that if you have the chamber, and let me go back. If you have the chamber, sorry, yes, if I've charged the chamber here, and then I put it down for a very long time, okay? If I put it down for a very long time, the cells, this thing will begin to dry. You know, that's the disadvantage of wet mounts. For wet mounts, they dry up very easily. So if this thing is drying up, where do you think the drying will start? The drying will start from the edge here. So you see that this place is dry, and as this place is dry, you see that it will push. Once it is dry, you will see that it is pushing or drifting the suspension further inside. So you see that this place is dry, but the suspension is here. All that is doing is that it is drying, but it is also pushing the cells further away. So that the cells that are here will have been influenced by the cells that were also here. Because it's drying, it is pushing its way up to this point. So that you see that the tumor cells here, those cells were actually all of them were supposed to be, let's say, somewhere here, and they would not have been counted. But remember, the ruling is somewhere in the center here, and this one is now drying. Once it's drying, it's pushing the suspension and the cells here. So there's going to be tumor cells loaded in the area of the counting area, and that is going to influence your count. I hope the point is clear. Good. Where delay after charging the chamber is unavoidable, the loaded chamber should be placed in a humid condition. Example, on straws within a petri dish containing a moistened. This one is also true for any wet mount. If you have, let's say, you've done some urine RE, you saw something, and let's say you want somebody to also take a look at it, and you keep it on the bench. By the time the next person comes in, probably it will have dried up. Once it dries up, you're likely to see what you saw. If you want to maintain it, what you do is that I'm sure all of us have at least, even if you're not in microbiology, you may have a piece of petri dish. These days, plastic petri dishes are a book. I mean, you can get a plastic petri dish anywhere, even if you're not in microbiology. So the plastic petri dish, what you do is that you can put in a filter paper, or even if not a filter paper, cotton wool. I mean, make it nice and flatten it to cover the base of the petri dish, and then moisten it. Put water on. I mean, moisten it, not water to make it. Flat it, but just moisten it. So if it's filter paper, you moisten the filter paper and put it at the base of the chamber, and then that's the chamber, the petri dish. All right. Then you apply a straw. I mean, it can be any of the straws that we use for the drinks. You cut it in a manner as that it will fit into the base of the what do you call it? The base of the petri dish. Remember, you have a petri dish, and then you put the bottom. You are putting filter paper or cotton wool. I mean, it's well spread, and then you've moistened it, so it becomes moist. And then you put a straw, 2 bars, okay, and then now the bar will serve as like a holder on which you place your what do you call it? You place your slide, and then you cover it with the cover slip. Sorry, you cover it with the top of the petri dish. It can stay for about 3 days. It will never dry up. So that if you have any wet mount. So what this is saying is that if you are doing, you have charged your chamber, and probably you have to, somebody has called you to come and see something. If you leave it, by the time you come, it will have dried up. And I will be saying that when it is drying, it will push the specimen into the area where you have the rulings, and the sperm count is going to be falsely high. But if you want to maintain it as it is, you have your petri dish. Either you use a filter paper or cotton wool or something that can take up water, and then you moisten it, and then you take straw. Even a straw, if you don't have straw, sometimes even in my lab, you can even use matches. I mean, just two matchsticks. Then put it in it, and then it serve like a bridge, and then you put your slide on it. You don't want the slide to touch the either the cotton wool or the filter paper directly. If you do that, you see that before you could say Jack, the water in it will somehow, some way, it will drift off the preparation that you have made. So if it is on a straw or anything that will prevent it from having a direct contact with the base, that is very well advised. So, like if you don't have a straw, and straw is like any of the straws that we use for Coca-Cola or whatever, they cut it so that it can fit into the base of the petri dish. And I'm saying that in my life, sometimes you even use matchsticks or broomstick. You just cut it to be able to fit into the listen. And then serve as a bridge, and then you put the other layer or slide or the chamber in it. When you cover it, I'm saying that it can stay for about 3 days and do not dry up. Okay, all right. So you know that now, so you'll be able to introduce the sample into the chamber. You must try to avoid overloading. Remember that as you are going forward, you're going to do the calculations on the volume that is going to be under the chamber. So if you overload it, you are going to create an excessive amount of fluid under the chamber, and that may not be helpful. You should also not to underload, okay, so that the thing must be loaded in a manner that it fits the entire chamber area well, no much, no less. You should try to avoid appearance of air bubbles. Okay, right. The cover glass being moved or displaced. This is why we say that when you are applying the cover slip, it might be affixed. It might be made in such a way that, in fact, I'll take to a technique called a Newton's ring. If you are able to fix it very well, you see some rings, rainbow rings, appearing at the edges, and that's called Newton's rings. And that is a confirmation that the cover slip is well fixed on the chamber so that it will not move. All right, but if you just place it anyhow, I mean, even as you load the chamber, it will slip off. Okay, you should try to avoid this. If any of these defects occur during or after charging the chamber, you must recharge. That's the repeat operation. So you say that you don't have to overload, you don't have to underload. There's air bubbles. The glass cover should not be moved or flipped. So if any of these things happens, you have to wash and then repeat the entire process. So in the sperm count, you use the times 10 objective lens and then close the condenser area sufficiently to give good contrast. You know that once that's good microscopy principles. Once you are using a times 10 to make an observation, times 10 don't need too much light. So once it doesn't need too much light, the condenser must be lowered. Okay. And there's something inside called the iris diaphragm. I'm sure you also know that. You must also close that one so that you are minimizing the amount of light that will be exposed onto the slide. That is for all microscopies and for all low power field examinations. So that's just that. So focus the rulings of the chamber and count the sperm within the 4 large corner squares, blah, 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 as you said. So now in counting, you are counting sperms. You are not counting head. You are not counting neck. You are not counting anything. So sometimes the question is, if I see a sperm head without a tail, should I count it? But the question is, are you counting a sperm or are you counting a head? The question is that the head alone make up a sperm. Yes, sir. So once you're able to answer these questions, you don't even need to ask me. So I've seen a tail without the head, should I count it? I'm sure that now the question you can answer that one. The question is, what are you counting? You are counting sperm. What makes up a sperm? A sperm is made up of a head, a neck, or a tail. You're not talking about the morphology. You're not saying that whether the head is big or small. That's one. But we are talking the fact that you have a sperm that has a head, a neck, and a tail. As to whether the tail is short, as to whether the neck is big, that is not what you're talking about. But you're not also talking about tails alone. If it's tail alone or head alone, it's not a sperm. So the question here that I'm sure you ask me, you should ask yourself, what am I counting? I'm counting sperms. If I've seen a head, should I count it? You are the best person to answer that question. Okay, so free tails, free hairs are not counted as spermatozoa because they are not sperms. Okay. When cells lie directly on or touch the line, use the counting rule to avoid cells being counted twice. So the question 2 is, what is counting rule? Right. So this is a good picture. So once you have your chamber like this is, let me see if I can get my, this is the area where you have the rulings. The great area is here. It's here. All right. And so it comes out to give you something like this. And this is the corner squares. Corner squares. Corner squares. Now, so if you take one corner square, for example, if this is the 4 corner square with 16 squares, this is 1, 2, 3, 4 here, 1, 2, 3, 4 here. This is 16 squares. If you are counting the sperms, and for that matter, cells, you take them one by one. So this square here, you are counting the number of cells here. You move to the next one, move to the next one. You come, when you finish, you come down here. Just as you're doing, if you're doing a wet mount microscopy for either urine or for stool, especially for stool, you must cover. As for urine, you can pick from various films. But for stool, you are supposed to count to scan the entire. Okay, so I'll come to that. I'll come to that. Whether those online will come to that. So if you have stool, for example, you are making sure that you are covering the entire preparation under the what do you call it? The cover flip, the entire area. And to be able to cover the entire area, you do this kind of style. You call it batterment technique. So you start from one end here, you go here, you get to the end, you come down, then you go here, come down, you go here. This is called a batterment technique. So you can apply the batterment technique in your counting so that you know that you have started here, you have concentrated on the cells here, you move here, you get to here, you come down so that you can cover the entire 16 squares. All right. Now, let's see. Somebody asks whether to count the cells on the line or not. Now, we are going to get to what we call the counting rule. The counting rule. Cells touching the top and left lines of the counting area are counted in. So remember that we said that and please, this is not just, remember we said that the principle around the counting chamber is the same for every count, whether it is CSF, body fluid, blood, semen, anything that's got to do with counting under the neighbor counting chamber. All the discussions that we talk about will apply. Remember this. This whole thing we are talking about will apply irrespective of whether it's semen or blood or CSF or any body fluid that you are doing accounting on. So take note. Don't say that, oh, you only taken through the CSF. Semen. So when even the CSF, that one they didn't teach us. Please, the principle, everything is the same. Good. So now remember we talked about the improved county chamber. The improved labor county chamber, I said that the ends of the area within which you have to count have triple lines, so that it guides you to know which of the squares are within the counting zone. So, for example, in this particular one, you know that this is a boundary. When you're going up here, this is the boundary. When you're going to the right, this is the boundary. When you're going down, this is the boundary. So that you know that you are working within this boundary. And this 1 to 16 squares are here. 1, 2, 3, 4, and then 1, 2, 3, 4. So this is the 16 squares at one corner. Okay. I think there was some song we say one corner, one corner. Do you remember? But this one is not like that. So this one corner will be 16 squares, and the triple lines I've told you, you get triple lines with improved counting chambers. The ordinary in labor counting chamber don't have these 3 lines guiding you as to where to go and where not to go. So it is up to you to decide to know that, oh, hey, I think I'm over counting, or I think I'm over going beyond the 16 squares. That's the difference with the improved and the ordinary labor. Otherwise, everything is the same. Now, the rules are that the cells on the top, so this is the top, and the cells on the left lines here are counted in. So that if a cell is here, it's on the left here, it is counted as though it is part of this square. Now, cells touching the bottom and right lines of the counting area are counted out. What it means here is that this is top and this is left. So they are counted in. And then cells right and then bottom are counted out. So that it means that when you're doing accounting, this cell will, if it's a sperm, it will not be added. This one will not be added. This one will not be added. This one will not be added because they fall on the right and bottom. That's what we mean about the counting rule. The counting rule says that when you are counting, cells on the left and top are included. On the top lines, they are included. Cells on the right and down are excluded. As simple as that. That is the rule. That's the rule. So when you are counting this one, for example, to be counted, so 1, 2, 3, this one will not be counted. Then you come here, nothing here. 4, 5, 6, 7, this one will be counted. And then this one, 8, this one will not be counted. This one will not be counted. 9, 10, this one will also not be counted. As simple as that. So the counting rule says that cells on the top and the left lines are counted in, that they are included in the count. Cells on the right and bottom are counted out, that they are excluded. I hope that answers your question. Good. So the same things here. So cells on the top and then on the left, they are included. So this one is a cell on the line on the left. It will be counted as part of this cell of this square. This one will be counted. This one will be counted. All these ones will be counted. This one will be counted, even though it's on a cell. But you see, the greater majority of the cell lies within the cell here, and so it will be counted. I hope that point is clear. Here, it is like 50-50. So it will be excluded. This one will also be excluded. This one will be excluded. So these are the conditions. This one, it is lying on this one, but my greater portion of the cell is within the cell. So this one will be counted. This one is like 50-50. it will be excluded. This one, majority is within the cell, it will be counted as part. This one will not be counted. So this one will help you to answer every question as to should it be included or should it be excluded. And you apply the counting rule. How the point is clear. That's the counting rule. Okay, good. Good. I'm saying that you see that all this while the emphasis has been on the four corner squares. And so you can count the cells in the four, and when you talk about cells, you're talking about the sperms, right? So you can count the sperms in the four corner squares, okay? And then as when it comes to calculation, you're going to do, so how do you calculate? You come to that. Then yes, also say that sperms can also be counted from the central, sperms can also be counted from the central live square area using 5 small squares in a pattern as shown below. So you remember that we said that in the central area, we have 25 small squares. And each of the 25 has been subdivided into 16. Now, so if it's 25, it means that this is the central square area. Let me get my touch. So you come to the central area. In the central area, you are going to get 5 here, 5 down. So that's 25 squares. So this 1, this 2, 3, 4, 5, still within the central area. Now, and then you can select 5 of the squares and count the sperms there. So this here will give, and then the central area. So the 4 corners plus the central area will give you 5. You can also go the diagonal way. If you go the diagonal way, it's 1, 2, 3, 4, 5. It's also acceptable. So in the central square area, you can concentrate on 5 small squares and count the sperms in there and use it for your calculation. And I'm saying that when we finish, at the end of the day, you see that you prefer to use the central area than the 4 large corner squares. And this one, I'm very, very sure about it. You prefer to use this one. So the central square area, take any of the, not any, but specified 5 squares, either 4 in the corners with the 1 in the center or 5 diagonally. So search for the calculation of sperm concentration. Remember, you can say sperm count or sperm concentration or even sperm density. Okay. That is not synonymous with total sperm count. Take note. We come to that. Total sperm count is not sperm concentration. People make a lot of confusion on that. Total sperm count is not the same thing as sperm count. It is not the same thing as sperm concentration. Sperm count is actually count per male. Total sperm count is count per the ejaculate. So you see that it is going to be your count per male multiplied by the volume, so that if somebody produces, let's say, 3.8 mils of the semen based on your calculation of the weight, you got 3.8 grams. It's 3.8 mils that he has produced. If he had, you did a sperm count and it is 10 million per male, then it means that his total sperm count is going to be the 10 million per male multiplied by 3.8. That's going to give you 38 point. Sorry, I mean, I'm confused, but I'm sure you understand it. It's going to be 10 times the volume. So if the volume was 3.8, and you and your sperm count was 10 million per minute, it's going to be 3.8 multiplied by 10. That's going to give you 38 million. So please, total sperm count is not synonymous with sperm count. The sperm count is synonymous with sperm concentration or sperm density. I hope you are not confused and you will never be confused. You have done your dilutions, you've done your charging, you have counted the sperms, and then now how are you going to do your count? To calculate the sperm concentration or count per mil, the following parameters are required. The following parameters are one, total number of sperm counted in the spare areas. We are not there yet now. But here we are talking about the 4 large quarter squares. You are going to do your calculation. I'm saying that in your calculation, what are the parameters that you need to be able to put together? First and foremost, you need the total number of sperms that you have counted for the 4 large quarter squares. If you had 10 here, 3 here, blah, blah, blah here, then you count them, and then that's the total number. You put that one down. So that is needed. And we call that one, not that we call that one, we designate that one as N. And where N is the total number of sperms counted in the 4 large quarter squares. 2, you need your dilution factor. Remember, you said that you necessarily have to dilute the specimen, one, to be able to reduce the number of sperms to manageable count. Most importantly, you also dilute to be able to reduce the viscosity that will allow for easy capillarity action. Okay. So for whatever reason, you are going to do a dilution. And remember that you want, if I diluted a certain specimen, please, I also need an answer here. I diluted a certain specimen, let's say blood. I diluted the blood 1 in 10. Blood, I diluted 1 in 10. And then when from the dilution, the one that I diluted, I counted, let's say, 100 red cells from the diluted specimen. What is the number of red cells in the original sample? Yes. Hey, our numbers are getting down all the time, is it? Good. This one there, oh, when you do this, you make me proud and you make me happy. Okay, so you are going to multiply the number that you got by the dilution factor. So if you make a 1 in 2 dilution, and then from that 1 in 2 dilution, you got 5. It means that the original sample, you must multiply the 5 by the dilution factor. Okay, good. So remember that in our semen, the sample that we got under the chamber was definitely diluted. Because if it was not diluted, you couldn't even have charged the chamber. So we are going to dilute. And when whatever number, the N that you got, the N is the number of cells from the 4 large corner squares. So that this N represents the diluted specimen. So the value of the N, the actual value of the N will be N multiplied by what? By the dilution factor. Okay, right. Then the next thing that you need will be the total volume of the chamber within which sperms have been counted. So these are the parameters that you need. You need the number of cells that you count from the 4 large squares. You need the dilution factor. You need your volume. Good. How do you calculate your volume? So let me see if, good. Now, let me see where the volume issue is coming up. Okay. Okay. Before, let's get this one before we go back again. So we said that we need the number of cells that we counted. You need your dilution factor. You also need the volume of the area that we counted. Remember that we counted the cells from the 4 large corner squares. So we must calculate the volume that we have used. Okay. Now, for each corner square, for this one, please, I'm going to do this one with all of you, so take note. What is the size here? The D. And we are using the D to represent the entire because the squares are the same all over. So what is the size of the D here? Yes, answer. The size of this, of the D here? What is it? Good, 1 millimeter. Good. So great. Iman Ramsey doing well. So, and then of course, because the square, if this 1 millimeter, this side is also 1 millimeter. So what will be the area here? The D. What is the area of the D? 1 millimeter square. Great. Hey, where do you come from? Good. 1 millimeter square. This 1 millimeter square. So this is also 1 millimeter square. This is also 1 millimeter square. This is 1 millimeter square. Remember that this side where we are doing the counting is below the cover flip. Do you remember that? We said that where we have the rulings is below, so that once you apply the cover slip, it gives you a depth. Okay, so the depth which is covered by the cover slip, whether it's here or here or here or here or here, the depth will be the same because the cover slip is uniform across. I hope you understand that one. So if this one has an area of 1 meter square and the depth is 1 millimeter, so the depth is 0.1, what will be the volume in this area? The volume in this area. Yes, let it come fast. The volume for D, the volume in this area will be what? The area is going to be 1 millimeter square, but it has a depth. Okay, it's covered by a depth of 0.1 millimeter, which we also know as the standard depth of the chamber. So once this one is covered, it means that you have an area and a depth. An area multiplied by depth or height gives you the volume. So what is the volume at the D? Good. So this gives you a 0.1 millimeter cube. Fantastic. Now, if this side is 0.1 millimeter cube, then it means that it's the same because the squares are all the same and they are all under the same cover slip. So they are also all under the same depth. Therefore, the total volume I will have occupied, I will have used up, did the counting, will be the 0.1 millimeter cube multiplied by 4. I hope you all agree with me. But the volume here is the same thing as the volume here, the volume here. And these are the areas that are counted. So the volume here, the total volume that I have used up in my counting is going to be 0.4 millimeter cube. Is there anybody who doesn't understand this one? So you all understand it. Good. So the total volume that I will have used is 0.4 millimeter cube. Now, so let's go back. In this example, our total, if assuming the blue distance are the sperms here, then it means that our total number of cells will be D will be 4, D will be what? 3, because this is out. D will be 3, F will be what? 1, 2, 3, 4. We are going to count this one. We are not going to count this one, but the counting rule. So this 4, this is also 3. So this will be our N will be the sum of all these ones. Okay. And assuming that we did a 1 in 20 dilution. Let's say we did a 1 in 20 dilution. So it means that from the corner squares, C, D, and F, these are the number of cells that we counted. Yes, only 14. Okay. You counted the 14 in what volume? In what volume? You counted the 14 in what volume? What's the volume that was used in counting the 14? Yes. Yes. The 14 was counted in what volume? 0.4. Great. Ima, you are on top of the issue. So these cells were counted in a total volume of 0.4 because this is 0.1 millimeter cube. So because the areas and the volumes are the same across, the total volume used up is 0.4 millimeter cube. So, and then we said, let's assume that we prepared 120 dilution for that particular test. Then, so this is the entire calculation for the total volume. Volume is area times the height or depth. Area of one large corner square is 1 multiplied by 1 millimeter. That gives you 1 millimeter square. The height is 0.1. Okay, so the volume for one large corner square is 0.1 millimeter cube. So the total volume for the 4 large corner squares will give you this. Exactly, you have gotten it perfectly. Good. So in our example, a total of 14 sperms is counted in the 4 large corner squares. This means that 14 sperms are present in a volume of 0.4 millimeter cube. Okay, so mathematically, this is expressed as x, which is the normal is the 14 in what? 14 in what? 0.4 millimeter cube. The 14 sperms were counted in a total volume of 0.4. So mathematically, it is 14 in the 0.4 millimeter cube. Okay, so 0.4 here, the entire expression here is a fraction, but this one is a decimal. So we must also convert this decimal also to a fraction, just as we did with the 20 microliters of blood and the 0.38 mils of the diluting fluid. To be able to work out, they must all belong to the same unit. So this something over something is a fraction, but some 0. This is a decimal. So you cannot mix the decimal with a fraction. So you must convert the decimal here also to a fraction. But we know that 0.4 is the same thing as 4 over 10, which is also a fraction. So if you come and put the 4 over 10 here, instead of 0.4, you put 4 over 10 here, then it becomes 14 over 4 over 10. You see that? So if you have 14 over 4 over 10, then the 10 which has come down will come up here to multiply. I hope that is mathematically acceptable. So this is 14 over 4 over 10. So it is like A over B over C. A over B over C is the same as A over B times C. So this is 14 over 4 over 10. Can now become 14 over 4 times the 10. So this is it. So the formula can be written as 14 times 10 over the 4. I hope this is also listen. So which is the sperm count per millimeter cube of the diluted specimen? Okay. Now you've said that this value is incorrect. Why? Because this is the sample, this is the expression in the diluted specimen. So to move forward, you have to multiply this whole thing by what? By the dilution factor. So we move forward. So you have to correct for the dilution factor. So to get the dilution factor, which is 1 in 20, if you have a dilution of 1 in 20, it means that our dilution factor is 20. So our formula now becomes 14 times 10 times 20. This 20 is the dilution factor over the 4. All right. So this becomes, if you work this one out, this one can, the 4 here will cancel the 20 here to give you 5. So it becomes 14 times 15 per millimeter cube. All right. I hope you understand up to this point. Good. Millimeter cube is the same thing as microliter. So this whole thing can be written as 14 times 50 per microliter. Okay, good. If there's any misunderstanding, draw my attention. We are trying to do the calculation, and when you finish, we can get a formula that will take us through. But I want you to follow it step by step so that you can derive your own formula. Good. Now, we're saying that sperms are counted in million per mil. Sperms are counted in million per mil. This one is 14 times 50 per microliter. This okay. Somebody wants us to take the formula again. So we are deriving the formula our own, so that once you sit down, when you finish, you do. I'm not going to go through the formula again like this one. The formula is now going to be written for you to now put in your figures. But I want you to know how you derive it so that you can also teach students. So we are saying that you did a sperm count. You did a 1 in 20 dilution. Okay, I'm sure you know how to do a 1 in 20 dilution. And when you charge your chamber, this is how the cells spread out. And when they spread out like this, it means that C contains 4 cells, D contains 3. You know that it is 3 because this one will not be counted per the counting rule. E is 4. Where's E? E is 4. How did I get the 4? 1, 2, 3. Where's the 4th one? Okay, so, and I think there was a mistake here. So, rather, sorry, but it will be the same. So, this is E. E is rather 3, and F is rather 4. 1, 2, 3, and 4. 4 because this one is on the line on the left line, and left line is included. Here is 3. So it is, I think I interchange the E and then the F. So the value will still be the same, the 14. So what it means is that we counted 14 cells in the 4 large corner squares. And we're saying that this 4 large corner squares has a certain volume. And the volume is the area here multiplied by the depth, which we know the depth of the chamber is 0.1. It doesn't change. So the volume here is 0.1 millimeter cube. Since the large corner squares are all the same, my 0.1 here can be multiplied by 4 to give me 0.4 millimeter cube. So what it means is that these 14 cells were obtained from where? These 14 cells were obtained from the volume of 0.4 millimeter cube. That is where you have the understanding is. The 14 cells here were 14 cells in the volume of 0.4 millimeter cube. Okay, so we move on. So the 14 sperms were counted in the 4 corner squares, which has a volume of 0.4 millimeter cube. So this is the statement. 14 sperms present in a volume of 0.4 millimeter cube. We want to write this statement mathematically. We want to write this statement mathematically. So forget about X for now. So the 14 sperms in this one means 14 over, because it's 14 in. In means a ratio is over. So 14 sperms in the 0.4 means that 14 over 0.4. And the 0.4 here is millimeter cube. You know where it is coming from, because each corner square is 0.1 millimeter cube. And the 4 corner squares will give me 0.1 millimeter cube multiplied by the 4. And that gives me the 0.4 millimeter cube. And that is where you had our 14 cells. So the 14 in the 0.4 will be the same thing as 14 over 0.4 millimeter cube. Okay. Then I'm saying that 14 over 0.4 is a fraction. But 0.42 is a decimal. So that it cannot work out. And I said that if you remember that when we said that 20 microliters of blood sample are been mixed with 0.38 mils of this, you know that you worked it out. And we're able to convert the 0.38 mils to microliters before you add it. So 0.4 is a decimal. And 14 over 0.4 is a fraction. So for it to be able to fit, you must convert the 0.4 also into a fraction. And all of us know that 0.4 is the same thing as 4 over 10 fractionally. It's 4 over 10. So in place of the 0.4, we are going to put 4 over 10. Okay. If you put 4 over 10, let me get this thing. If you put 4 over 10 here, 4 over 10 here, it's going to be 14 over 4 over 10. And I'm saying that 14 over 4 over 10 is the same thing as saying that A over B over C. And mathematically, if you have A over B over C, the C can be moved up to go and multiply the A. So it becomes A over B times C. That is a basic mathematical expression. So if you have 14 over 4 over 10, then it means that the over 10 down here will go up here to multiply. So it becomes 14 times 10 over the 4. I hope the point is clear. And the millimeter cube is still important because that is the unit. Okay. Then we say that this whole thing is the number of cells that you are getting from the 4 large corner squares. And before you can get cells in the 4 large corner squares, you ought to have diluted. So this 14 that you got was gotten from the diluted sample. And you said that whenever you dilute, to get the actual number, you have to multiply by the dilution factor. So we had 14 here. So the actual number will be this 14 should be multiplied by the dilution factor. And we said that with this particular example that we did, we had a dilution factor of 1 in 20. So that our dilution factor is 20. So we must multiply the 14 by 20. Because when we use the 14 is the number of cells you got from the diluted specimen. So for the undiluted specimen, you must multiply this 14 by the dilution factor, which is 20. So the whole thing now becomes 14 times this 10 times the 20 before the over 4 will come. I hope this point should be clear by now. So this is where the whole thing is now. It's now 14 times 10 times the 20 over the 4. Okay. Now, so this is the entire data. But the unit becomes per millimeter cube. And I'm saying that now, semen is reported in per mil, not in per millimeter cube. So you must convert this millimeter cube to mils. But before you can convert this millimeter cube to mils, you must first of all convert it to microliter, because millimeter cube is the same thing as microliter. So this whole thing can be written and replaced with microliter, because millimeter cube is equivalent to microliter. So when we multiply this, let me take you to this point. Now you've got, you know where you how we got here. Okay. So some people take the formula from this point and say that your total count, your total count, 14 here is the number of cells that you counted. 10 here is the depth of the chamber. You remember the depth of the chamber is 0.1. And if you have 0.1, 0.1 is 1 over 10. So if it's 1 over 10, they use the 10 as your depth of the chamber. So this is the depth, the 10 here becomes the depth of the chamber. What is the 20 here? Yes, you can tell me. The 20 here. The 20 here is what? You can tell me. Great, the dilution factor. Okay, so even though, look at where we started from up to this point. But I'm saying that some people, very good, dilution factor. Some people will not start from where we started from. We'll just start the formula from this point and say that the sperm count is your 14, which is the number of cells. So they write N. So the 14 is the number of cells, the N, times this, which is the depth of the chamber. Depth of the chamber is 0.1, and they make it 10, 1 over 10. So they make it 10. So the depth of the chamber, this is the dilution factor. And this 4 is the 4 areas you counted. So some people will just not start anything. They will just say that, okay, the total, your sperm count is the number of cells multiplied by the depth of the chamber, multiplied by the dilution factor over the area counted, period. That's all. Then they end there. So, but I'm just taking you through to know how we got here. And I'm sure that at least some of you will have understood up to this point how we got here. And how we got here is where people take it from there. at the beginning of the formula. And it's also true. So when you are working, you don't need to go and start from a fresh and come here. So in examination time, oh, you do yourself a sperm count. You just write your my sperm count, my X is going to be number of cells I count multiply by, and this one will be the 10 here will always be constant because the depth of the chamber will never change. The 20 here may change depending on your dilution factor. But most times your dilution factor, you may make it 1 in 20. So the 22 will be here. And then over the area here too will not count because will not change because you are always using the number of what do you call it? The areas you are counting, which is 4 like corner square. The 4 was so this one will not change. The 4 will not change. The 10 will not change. The 20 may not change. The 14 will change because this is the number of cells they are counting. So you put here n times 10 times 20 over 4, and you are free to go. Here I did the calculations and I got 14 times 50 because the 4 will have cancelled the 20 to give me 5. And then you multiply the 5 by the 10, you get 50. So it is that 14, which the number of cells multiplied by 50 per millimeter cube. And you know where the millimeter cube is coming from. And we're saying that since we want our result in per mil, you must convert this one to per mil. But you can't change it direct. So you first have to change it to microliter. Fortunately, 1 microliter is equivalent to 1 microliter is equivalent to 1 millimeter cube. Therefore, all we need to do is to replace the millimeter cube here by microliter. So the 14 times 50 per millimeter cube can be written as 14 times 10 per microliter because millimeter cube is equivalent to microliter. So now that we know that we want to convert our result to mils. Remember, we want to convert our result to per mil, not per microliter. But you know that 1 microliter, if you want to convert to per mil, 1 microliter is 1,000th of a mil. So 1 microliter is 1 over 1,000 per mil. So I wish this one were physical, then you can understand it better. So 14 times 50 per microliter. This one, you know where it is coming from. This one, you know this one. 14 times 50 per microliter. You know up to this point. This is where you are carrying it forward. So this one comes up to 14 times 50 per microliter. So this is the 14 times 50. Now, per microliter is to divide by 1,000. But you see, because the per microliter is down here, and microliter is the same thing 1 over 1,000. So for the mil, it's 1 over 1,000. It means that the 1,000, which is going to come, now will have to come to multiply the 10 times the 50. Please take note of this one. Those who are mathematically, I'm sure they will get this one fast. So the per microliter is the same thing as 1 over 1,000 mils. So we are going to replace the microliter here by 1 over 1,000. So the 1 over 1,000 down here, the 1,000 will go up to multiply. So the whole thing becomes 14 times 50 times 1,000, and then the per mil will come. Okay, the per mil will come. Now, there's something here we're going to manipulate. Look here. Look here. So you now understand that the 1,000 here is coming from the microliter because the microliter is 1 over 1,000. And it will change to per mil. So 1 over 1,000, the 1,000 will go up to multiply. So it is 14 times 50 times 1,000. Then it will come to per mil. Okay. Now, we're saying that semen is reported in million per mil. A million means 10 to the power 6. Watch here. Million means 10 to the power 6. So you have to manipulate. I'm using the word manipulate. You have to manipulate to get 10 to the power 6 up here. You already have 10 to the power 3 here. You have 14 times 50. So as for the 14 is the number of cells that you are counting. So you can pattern that that one because that can change. This 50 has come here. You can manipulate this 50 to give you 10 to the power 3. Because you have 10 to the power 3 here, you need another 10 to the power 3 so that the whole thing can become 10 to the power 6. You know that 10 to the power 6 is million. And you know that I'm saying that sperms are counted in million per male. That is the standard, million per male. You have gotten your per male here. So you must get your million. A million means 10 to the power 6. You have 10 to the power 3 here. So what do you do to get another 10 to the power 3? So what you do here is that this is 50. So 50, if I replace the 50 by 1,000 over 20, 1,000 over 50 is what? Yes, you can tell me. 1,000 over 20 is what? 1,000 over 20 is what? What is 1,000 over 20? Yes, it's 50. So if I have 50 here, and then I come and put here 1,000 over 20, I haven't done anything wrong. So in place of the 50, I'm going to now write 14 times 50. I'm now going to write 14 times 1,000 over 50. Sorry, 1,000 over 20. It is the same 50. But to make my mathematical expression, I have to now change the 50 to 1,000 over 20. If I change the 1,000 over 20, it is the same as my 50 here. So now I'm not going to get 14 times 1,000 times 100,000 over 20. So now I can now bring it here mathematically. I can bring the 14 here and I'll bring my 20 down here. So my 1,000 and the 1,000 here can stand out. So I can get 14 over 20 times 1,000 times 1,000 and 1,000 times 100,000 give me 10 to the power 6, which is million. So the whole thing now becomes 40 over 20, and 40 over 20 is what? 40 over 20 is 0.7. And then so it's 0.7, and then I get my 10 to the power 6, which is million, and then I get my per mil. So it is a mathematical, a nice way of trying to manipulate the thing to fit into the rules of expression for a sperm count. Sperm count is expressed as million per mil. That is, you can't change anything about it. Million per mil. So you have to do the manipulation to get into the million per mil. Unfortunately, you're able to do and get the per mil. How do you get your million? So you have to also manipulate. Thank you, Ramsey. Thank you. So that is how it is. So you know your target. You have to get your result in million per mil. That one, me and you can't do anything. But that is the WHO standard of reporting sperm count, million per mil. From your calculation, you are going to get something per millimeter cube. Per millimeter cube because the chamber will give you a volume in millimeter cube. And that one, you can't do anything about it because the squares are in millimeters. Have 1 millimeter plus another 1 millimeter, a depth to another millimeter. So you are going to get millimeter cube. That one, you can't do anything about it. But you know where you are going. You are going to million per mil. So any way possible for you to manipulate to get the million per mil, you have to do it. And that's how far you have come. I'm sure that if you get a slide and then for the explanation, I'm sure you can manage it. Let's see some other examples, and then so derivation of the general formula. A thorough understanding of the formula to calculate sperm count is very necessary and allows for some kind of flexibility. The following parameters may vary for each sperm counting. What are the parameters that can vary? The parameter that can vary can be the volume. Because you can decide, for example, you can decide to count the cells, like I've said, from the what we call a central area. If you decide to count the cells from the central area, your volume will change. If you decide even to say that, okay, I'm going to count the cells in only 2 squares, your volume will change. Okay, so once you understand the whole thing, whether the volume changes or whatever changes, you can still get your way through. And then the dilation factor will change depending on your initial microscopy. I'm saying that initial microscopy is very, very important to let you determine appropriate dilation factor. So if, let's say, you have, for example, the example that I gave you, our dilution was wrong because if you did your wet mount and then you say that, oh, we are going to do a 1 in 20 dilution, it means that the sperm count was going to be significant. But here we had four in one corner, 3 in one corner, 4 in one. It means that our dilution factor was just wrong. But it was just for example's sake. Okay. So for that particular case, for example, probably 1 in 4 dilution will have been better. So if you do a 1 in 4 dilution, the cells will not be too much diluted, and therefore the count will be very much well appreciated. So I'm saying that certain things will change, but those things that will change, you will still have a hold of it. You still can manipulate it. Right. Now, so the derivation, we have known where you are coming from. Okay. And then now, so if you are doing the thing, you don't need to go back, but even though you can go back, but the short formula which you have derived, and I'm sure you understand it now, is your sperm count, which is X, will be the number of sperm that you count multiplied by the dilution factor over the volume. So initially, the depth will not come here because the depth will be a factor of the volume. So if you say n multiplied by the depth of the chamber multiplied by the dilution factor over the v, then there will be a duplication because the v here takes into consideration the depth of the chamber because the v is a product of area and the depth. So you can't say that it's n multiplied by the depth of the chamber multiplied by the dilution factor over the volume. That one will be wrong. I hope that you have understood me. All right. So either you say is the number of cells multiplied by the depth of the chamber multiplied by the dilution factor over the area. And then in that case, this one will not be millimeter cube. If you say over the area, this one will not be millimeter cube. And then that can also create another problem for you. So for now, the easier way is to say that is the number of cells that you count. This number of cells will necessarily have to multiply by the dilution factor. You know this one, that whenever you do a count, this count is done under the chamber. But before you do this count, you ought to have diluted. You necessarily, so whatever this n is the number of cells in the diluted specimen. So for you to do your count, this n must be multiplied by the dilution factor. Okay, so this is where you have your denominator, sorry, your numerator. And then this one is in a certain volume. This is your V in millimeter cube, and the volume will be in millimeter cube. And this one will help you to convert to the microliter because millimeter cube is the same thing as what? Microliter. And then microliter can easily be converted to per mil. And then now easily you're moving to the arena of the standard for count sperm count. So of course, where n is the number of cells, total number of cells counted, df is the dilution factor, the volume, the area counted, right? So it comes back to this point. Now, we say here that the millimeter cube should be converted to microliter because millimeter cube is the same thing as microliter. So in place of the millimeter cube, you can put the microliter. Now, if you put the microliter, you can also convert to per mil because you know that microliter can be converted to mil by dividing by 1,000. By dividing by 1,000 means here that this is already dividing here. The millimeter cube is already divided. So to divide by 100,000, 1 over 1,000, the 1,000 will go up here to multiply. So this whole thing becomes n times the dilution factor times the 1,000. So the top 1,000 here also becomes constant over your volume, the volume that you are going to use. And then here now, this place now, once you have multiplied here by 1,000, this place will become what? You can tell me. Once you have multiplied the DF by 1,000, what will be this place? You can tell me. This place will be what? If I multiply here by 1,000, the DF by 1,000, what will this milliliter cube be? Very good. Male. And if you say male here, it will like million. It's like male, it's ML. Okay, very good. That's good. That's good. So this place now becomes per male. Then it means that you are satisfying one aspect of the game because you want your result in per male. So your male will come here. Okay. Then you struggle, you manipulate to get a million because whatever you get, your result should be reported in million per male. Million per male. So as soon as you are able to now get here times 1,000 and per male, then 1,000 has also given you a certain baseline, 10 to the power 3. Then you manipulate the rest to get under 10 to the power 3 to satisfy your million, which is 10 to the power 6. So that is the way to go. And whenever you are able to do that, it will always be cheap. So now let's do this. I'm sure you know this, you are very familiar with this formula. Okay. Then it comes to an example where we do a 1 in 20 dilution. Okay. We do a 1 in 20 dilution. So now your sperm count will be the number of cells multiplied by the dilution factor here. Dilution factor over 0.4. The volume that we counted is 0.4. This one, 0.4 milliliter cube. So it becomes number of cells, and then 0.4 here too is the same thing as 4 over 10, like we said already. So the 4 over 10, the 10 that's going to come down, come up here to multiply. So it becomes n times this 20, which is your dilution factor, times the depth here, and then this one comes here. And we're saying that this milliliter cube is the same time macroliter. So now this whole thing can be brought down here to n times 20 times 10 times 4 per macroliter. Then it comes back again that, so we want to convert the macroliter to per mil. And then we say that per mil is divided by 1,000. So divided by 1,000, 1,000 will go up here to multiply. So that gives you 10 to the power 3 here. Okay, so you have this one. Now, if you like, at this point, you don't have to divide anything. You don't have to divide anything because we say that you have your per mil here. Okay, the mil is here. You want 10 to the power 6 to satisfy the million. You have 20 here, you have 10 here. You ask yourself, what can you do here? If I multiply here by 5, okay? If I multiply here by 5, what will I get? I'll get my 1,000, isn't it? But if I multiply here by 5, I will have disturbed the equation. So I multiply here by 5, and I multiply down here by 5. So what it means that I must multiply 2 by 5 over 5. If I multiply 2 by 5 over 5, then this side gives me my 20. And then this side gives me my 10 to the power 3. And this whole thing gives me my another 1,000. Okay, so I'll get my n times 10 to the power 3 times another 10 to the power 3 over my 20 mil here. And then now I satisfy my 10 to the power 6 here. So I take it out. And then the n becomes n over 20. So n over 20 times 10 to the power 6 per mil. So what it means here is that if I do a dilution of 1 in 20, and I do the sperm count in the 4 like corner squares, all I have to do is that I forget about everything, and I'll say that the number that I got, if I got 200 here, I'll divide 200 by 20 and add million per mil. So I get my 200, which is the number of cells I got from the 4 corner squares. Divided by 20, I got 100. So my result will be 100 million per mil. You don't need to so you go through all these ones to be able to understand how come you got the n over 20. and probably for students' education. But in your day-to-day work, you don't need to worry yourself. You know that if you do a 120 dilution, you get n divided by 20. Now, so I've made a summary for the dilutions. So if you do, so these calculations of sperm count in million per mil for different dilutions. So if you do a 1 in 2 dilution, and that case means the sperms were just scanty. So you did a 1 in 2 dilution. 1 in 2 dilution means one part of the sample plus one part of the diluent. That will give you 1 in 2. And that will give you a dilution factor of 2. 1 in 2 is the dilution factor of 2. If you do a 1 in 2 dilution, if you do the calculation, you can take your time and go through the process as we did. You see that you get n over 20. So if you do, sorry, n over 200. So if you do 1 in 2 dilution, the number of cells that you get, okay, divide by 200, and then just add million per mil. If you did 1 in 4 dilution, n over, so if you do you see that this one will catch up with if you do 1 in 20, you get n over 20 million per mil. If you did 1 in 80, you get n over 50. At this point, can I ask somebody to work out if you do a 1 in 100 dilution, what will be your formula? Anybody who can work it out for me, I think I will mark the person down for an extra mark. If you did a 1 in 100 dilution, what will be your abridged formula? So those 2.5, no, please, it's not the answer. Come again, you take your time and do it. You get it. It's very, very simple. Very, very, very simple. Try it, please. Come again. It's very, very simple. You will get it. No, no. Let me come again. I don't know where the problem is coming from. This is the simplest calculation you could have ever made. Okay, so you can start from this point. Okay, let me. It's the easiest. I thought that you get it. You get it. This thing. It's coming. Great. Ima got it. N over 4 million per mil. Great. Everybody clap for Ima for me. Ima made it. N over 4. And it's very simple. Thank you, Ima. I will do the needful. Okay. Good. So I'm sure you all understood up to this point, at least up to this point. Okay. This point is clear because at least up to this point, you have converted to the per mil. You have converted this place to the per mil. Okay. You have converted this place to mil. So, and for the mil side, you will have noticed that you have your 10 to the power 3 here. Okay. Now, I say you make a 1 in 10 dilution. Remember that the 0.4, the 10 here has come as a result of the 4 over 10, and the 10 has moved up here. So you can't change it. This is part of the volume. The 10 here is part of the volume. What you can change is the 20, because this 20 is the dilution factor. And our dilution factor is now what? Our dilution factor is now 100. They say you have made a 100 dilution. So this one is 100. So if this one is 100, straight away you get 100 times 10. That is already another 1,000 altogether. So you have 100 here and 10 here. This 10 to the power, this 1,000, another 10 to the power 3. So this is the simplest calculation I expected anybody to do. So our dilution factor is now 100. This 10 is constant because it is part of the volume, which is 0.4. And the 0.4 we have converted to become 4 over 10, and the 10 has come up. So this 10 to you can this is what I'm saying, that people say that this is the depth of the chamber. Okay. All right. So this 10 is there. And then this 20 has now become 100. So once this has become 100, this is 10, this is a cool chop. 100 here and 10 here is already 1,000. And then 10 to the power 3 is also already here. So this gives you your, this entire whole thing here gives you your what? 10 to the power 6. And therefore, now is the only one which is left. So it becomes N over 4 million per mil. So this shouldn't even give anybody any headache. This shouldn't give anybody any headache at all. Please take your time and master the process. It is very, very simple. Very, very, very simple. Very, 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 very simple. Okay. Right. And I've said over and over again that these calculations and manipulations is the same for WBC count. So if, for example, you're also doing a WBC count, okay, and in that case, you are supposed to report in 10 to the power 9 per liter. 10 to the power 9 per liter. So 10 to the power 9 per liter 2 is also a constant. That is the standard for reporting WBC, 10 to the power 9 per liter. If you are doing these calculations, you should be able to do it. You see, let's go back. Assuming that you're doing what do you call it? WBC count. Okay. And WBC count, you said that normally you will have done what? 1 in 20 dilution, because they will take 20 microliters of blood and then 0.38 mils of the diluting fluid. That works out to give you a dilution factor of 1 in 20. So that is there. Good. It's the same chamber, it's the same four corners, it's the same everything. So we can use the same formula here. So the N here is the number of 5 cells you count. Dilution factor will become 20. Okay. Now the the V here says 0.4 because we are going to use the same 4 corner squares. Okay, so it will give you this formula. It will give you this formula. Okay, all right. And then it will also give you this formula. Okay, I hope you are following me. I'm saying that I don't want to go back, but it is the number of cells times dilution factor. Dilution factor is 20, and then volume 2 is 0.4. So it's the same thing. N times the 20 is the dilution factor over the 4 over 10. So it is the same thing here. And then you want our results in something times 10 to the power 9 per liter. Watch carefully. So it is the same up to this point. Up to this point. Up to this point. I'm sure you follow it up to this point. Okay. Then here, this is where the mathematics change. Now, here is per mil. I hope you are getting me. This. I'm talking about the WBC count. How come you report 10 to the power 9 per liter? Now, this is 10 to the power 3. We are reporting in per liter. We are reporting in what? Per liter. So we must also convert the mils here to liter. Is that not it? If you convert the mils to liter, what are you going to do? We are converting per mil here to per liter. What must we do? Who can tell me, please? Our time is gone, power. Who can tell me? We have per mil here. I'm saying that we are doing classical WBC count. And you want to know how come you are able to get 10 to the power 9 per liter using the chamber. And I'm saying that at least we are up to this point, you understand how come we are here. But WBC is reporting per liter. And this one is going to give us something in per mil. What must we do to get the per liter here? Very good. Very good. Ima is mathematically inclined. So this per mil to here, it should also be like divided by 1,000. You are supposed to be 1/1,000 to give you the per liter. So to divide by 1,000, you are going to get the 1,000 up here to multiply. So you see that you are going to get 10 to the power 3 is here. You're going to get it times another 10 to the power 3. So if you are getting 10 to the power 6 here, okay, so it's going to be n times 20 times 10 times 10 to the power 6 over 4. And then the per liter will come. I hope those who are following me will appreciate this one. As the same thing here, but now the per mil is going to be converted to per liter. Per liter means you must also divide by 1,000, 1/1,000, and then 1,000 will come here to multiply. But you have 10 to the power 3 here already. So if you have to multiply by another 10 to the power 3, you give us 10 to the power 6. And then the down will convert to the per liter. So in that case, you have n times 20 times 10 times 10 to the power 6 over 4. Then you do your manipulation. So if you do your manipulation, I'm going to multiply top here by 5 and multiply down here by 5, just as we did with this one. Okay, just as we did with this one. If you do that one, if you multiply the top here by 5, you are going to get another 1,000 here. I hope you are following me. You are going to get another 1,000 here. So the 1,000 here will now add up to here has become 10 to the power 6. So you are going to get 10 to the power 9. Now this 4 here, what must we do to the 4 here? Who can tell me? Who can tell me? What must we do to the 4 down here? Yes, Ima. What must we do to the multiply by 5? Great. So if you multiply by 5, this place now becomes 20. So it becomes n over 20 times 10 to the power 9 per liter. So because 10 to the power 3 here, we have converted here another from the mil, we have converted another 10 to the power 3 here. So we've got 10 to the power 6. And here we have multiplied here by 5 to get another 10 to the power 3. So we have been able to create 10 to the power 9 here. Once we create 10 to the power 9 here, because we multiply the top here by 5, we must multiply down here by 5. So this one will give us 20. And this mil is no longer mil, it's rather liter. So the whole thing now becomes n over 20 times 10 to the power 9 per liter. So if you are doing the normal WBC count with the chamber, you have been able to create 10 to the power 9 per liter. Here, you have been able to create this place to become 10 to the power 9 per liter. So the number of cells, white cells you count in the area, you divide by 20 and then add times 10 to the power 9 per liter. That's how it is. That's how it is. So if you do any WBC count with the chamber, any WBC count, if you did the 1 in 20 dilution, okay, then you work it out. Whatever number, if I got 130 cells, 130 cells will give me 6.5 because 130 divided by 20, that will give me 6.5. So I just write 6.5, then add my times 10 to the power 9 per liter. That's all. That's all. And as scientists, we are losing something out. You see, sometimes if you have a leukemia case, the machine, sometimes some of the machines are not able to do dilution. Because some of the machines are able to do dilution if the count is too much, that machine is able to dilute and recount and give you the value. Some of the machines lack the dilution effect, the dilution principle. So what they do is that if the WC is too count, you see them there, the machine will just indicate X, 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 X. It means I can't count. If it can't count, what the lab scientist is supposed to do is now go and do a manual count. And in doing the manual count, what it means is that if you do the normal 1 in 20 dilution, it will also not work. If you do the 1 in 20 dilution and you're going to use the WBC chamber, the sperm, the process are going to so much that you can't count. So you do your 1 in 20 dilution, all right, and do a further, what do you call it? Let's say 1 in 5. If you do 1 in 5 from the 1 in 20, you're going to get 1 in 100. This 1 in 100, it means your formula of n over 20 times 10 to the power 9 per liter will change because your dilution factor has changed. And so you have to go back and fix it into the formula. And now your n times 20 has now become n times 100. Okay. And then you work it out and you see that you come back to n over 4 as we did for this thing. N over 4, and then it's still going to be n over 4 times 10 to the power 9 per liter. Okay, so once you understand the principle, ladies and gentlemen, it is the same for every count that involves the chamber. And I'm sure that you can take your time and go through some of these things on your own. And when you have a challenge, please don't hesitate to call on me. Right. So sperm count using the central, you finish with this one, and then we go. The sperm count using the central area. Now, here is the same thing that, and this also, like I've said, very, very simple. Now, let's go back. Good. Here, now you realize that the square here, where we have blackened it, are the area which was used for platelets and then for RBCs. This is the area you want to use for sperm count. What is the area? 1 square where you have this. I'm sorry, I've overstretched you, but sorry for that. This square, what is the area here? Who can tell me? The area here. You have done it. Yes. Somebody wants us to continue tomorrow. Okay, so let's try and finish this one then. So here, remember 0.2, very good. It's not 0.2 millimeter square, it's 0.2. This is 0. Because this is 1 millimeter divided by 5, because this is divided by 25. So 1 divided by 5 will give you 0.2. So this side is 0.2. So this area here is 0.2 multiplied by 0.2. This will give you 0.04 millimeter cube. Okay, sorry, millimeter square. And with this millimeter square, the depth is still the same, 0.1. So that is going to give you 0.004 millimeter cube. Those of you who are mathematically listening, this is 0.2. Multiplied by 0.2 will give you 0.04. Okay. The depth of the chamber is 0.1. The depth of the chamber is 0.1. So the volume here will be what? You can tell me the volume here. This is 0.2 multiplied by 0.2. This will give you 0.04. The depth of the chamber is 0.1. So what will be the volume here? Yes. The volume here will be what? Good. 0.004 millimeter cube. Great of you, Harry. Now, we are using 5 of these areas. 5. 1, 2, 3, 4, 5. So what will be the total volume that you have used? What will be the total volume? This is 0.004 millimeter cube. We are using 5 areas. 5. So what will be the total volume? 0.02 millimeter cube. Great. 0.02. Very good. Let's now go into our formula. Now, by our formula, this is the number of cells that you count. I say we need to do a dilation factor of what? 20. So it is going to be n times 20. Please take your pen and papers. N times 20. And our volume is, the total volume we have used is what? 0. The volume you use, yes. The volume you use is 0.02. Okay. The volume you use is 0.02. And 0.02 by fraction will give you what? 0.02 by fraction. Very good. 2 over 100. So because this place is now going to be 2 over the 0.4 is now going to be 0. Good. 2 over 100. So because this place is now going to be 0.02, it is going to now become 2 over 100. And then 2 over 100, 100 will go up here to multiply. I hope that you are following this. It's the same formula that we are working out here. So it is n times the 20 times 100. Okay, 20 here multiplied by 100, because now this place is now going to become what? This place is now going to become 2. And this place is now going to multiply by 100. And once you do this one, you will realize that let me make it more simpler for you here. Here you have our 10 to the power 3 here, okay? And this place, this place has become 2, okay? And now 20 is here because 20 is the dilation factor. And this place has become 2. And then we have 2 over 100. So this place has become 100. So if this place, the 10 here has become 100, and this 22 is there, and we'll have 2 here. The 2 here will cancel the 20 here and give you 10. Is that not it? So if you have 10 here and this place has become 100, you have already also gotten n over what? Sorry, and you have already gotten 10 to the power 3 here. You take your time. I know Harry can work this one out. This 10 to the power 3, they have gotten it already. This 4 is now 2. And this 10 has become 100 because it's going to be 0.02. And because there's 0.02, the fraction will become 2 over 100. And the 100 has come up here. Once the 100 has come up here, you are left with 2 here. The 2 will cancel this 20 to give you another 10. So the 10 multiplied by the 100 will give you another 10 to the power 3. So you see that there's nothing here except the male. And this whole thing has become what? This whole thing has become 10 to the power 6, which is million. So what it means is that if you use the 4 and the 5 squares, in the central area. It is N, and you don't do anything about it. It's N million per mil. N million per mil. I don't know whether Harry should be able to get this one and probably take his time to take the rest through. I'm saying that it's the same formula here. You know where you are, why you got the 10 to the power 3 here, because you converted the millimeter cube to microliter, and you converted the microliter to mil and multiply here by this thing. I'm saying the 4 here is no more 4. It's rather 0.02. And the 0.02 will give you 2 over 100. The 2 over 100, the 2 will remain here, and the 100 will go up. This 20 is our dilation factor. So the 2 which is here will multiply, will divide this 20 to give you 10. And the 10 here will now multiply this 100, which is coming from the 2 over the 100. So this one will give you 10 to the power 3. 10 to the power 3 times another 10 to the power 2 will give you 10 to the power 6. So we are covered with the million, and the mil 2 is already here. So when you do the 5 squares within the central area, you don't add anything, you don't subtract anything, you don't multiply anything. Whatever value, if you got 13, it's 13 million per mil. If you got 500, it's 500 million per mil. As simple as that. I hope that makes things even more simpler. And so if you do the your dilution for this one is sperm count using a central square area. You do your 1 in 20 dilution. Count the 5 RBC in quotes, RBC counting areas. 4 at the corners and 1 in the center. That will give you 5. If you do the calculations, if suppose the sperms were 50, if you do the calculations, it will give you 50 million per mil. That's all. And this is very, very, very simple. So you charge your chamber, under the chamber. Now, instead of the 4 corner squares, you are now going to concentrate on the 5 small squares within the central area. Okay, you do your count, and whatever number of cells that you get, whatever number of cells is, the X is million per mil. And this is the end of the count. So I think we are done. We are left with terminologies. And that one I'll share with you on the platform, or I can add to the notes and give it to you. Thank you. We have all of us stressed ourselves. Thank you so much. Hopefully, God willing, on 23rd, I'll see you in Accra. And if there are any personal questions you have to ask, I'll be available for you. Thank you so much. God bless us all. Good night.